Why aren't stars enough to explain galaxy motions? How was dark matter first discovered? What holds galaxies together? Picture yourself lying on a gentle hillside beneath a clear night sky. The ground beneath you is cool and steady, and a soft hush envelops the world around you. Above, countless stars shimmer like tiny beacons against a vast canvas of darkness. Each pinpoint of starlight feels ancient, having travelled across the universe to reach your eyes. The night air is still and calm, and in this moment you feel deeply at peace, cradled by the vastness of the cosmos. As you gaze upward, you notice a faint milky band of light arcing overhead. This is the Milky Way, our galaxy seen from within, a river of countless distant stars flowing across the sky. It glows softly, a hazy swath of starlight in the darkness. For millennia, people wondered what this band was, and only recently did we learn it is the combined light of billions of stars. And yet, even this glorious congregation of stars is surrounded by something more profound, an even greater expanse of dark, seemingly empty space. In the quiet darkness, you might think there's nothing at all between those stars. After all, the stars and galaxies capture our gaze with their brilliant light. For centuries, we believed that the space between those lights was truly empty, tranquil, silent, a perfect void. Darkness was simply the absence of light. But as we gaze deeper into the night, a gentle question whispers, is the darkness truly empty, or could it be hiding something unseen? Starlight shines like glittering dust on black velvet, yet something about the way it scatters hints at hidden shapes within the darkness. Imagine space as a vast ocean, and the galaxies as boats drifting upon it. We cannot see the gentle currents beneath the surface, but we notice their influence as the boats sway and move. In much the same way, the stars reveal subtle hints of an invisible presence. There are shadows in the starlight, not ordinary shadows cast by light, but whispers of something invisible shaping the cosmos itself. For a long time, our understanding of the universe was painted only with the colours of light we could see. Ancient sky watchers connected the stars into constellations and wove stories about them. Through telescopes, we discovered glowing nebulae, bright star clusters, and distant galaxies swirling like luminous whirlpools. It seemed that everything we knew about the cosmos came from the light those objects gave off. It was comforting to think that if something did not shine or reflect light, it simply wasn't there. The darkness in between was just empty space, or so we thought. But as our curiosity deepened and our instruments sharpened, little by little we found clues that the darkness might not be so empty after all. The universe's behaviour, we realised, could not be explained by the glittering stars alone. There was more gravity out there than the visible matter could account for. Galaxies were moving and spinning in ways that defied our expectations, almost as if an invisible hand were gently guiding them. It felt like the cosmos was holding on to a secret, something vital, yet hidden in plain sight. You can imagine how puzzling this was. Picture watching a carousel on a distant hill at night, its lights twinkling as it spins around. If it spins faster than expected, you might wonder if there are more riders on board than you can see in the dark. Similarly, astronomers looked at the way galaxies spin and how clusters of galaxies move, and they realized something didn't add up. There had to be more mass out there, something unseen. Otherwise, those cosmic carousels would fly apart. It was a profound mystery, waiting quietly in the dark. And so, a cosmic detective story began. To find whatever lurked unseen among the stars, scientists could no longer rely only on light, but had to listen to the subtle whispers of gravity. The universe was whispering its secret through the motions of celestial bodies. Those who listened carefully started to suspect that most of the matter in existence was invisible to our eyes. They began to call this unseen mass by a simple, intriguing name: dark matter. In this calm night of our imagination, as we drift among the stars, we too sense that secret presence. We can almost feel a faint gravitational embrace, as if the darkness itself were gently cradling the stars. What could be out there, holding the cosmos together in these shadowy arms? To answer that, we will follow the journey of discovery, the search for the universe's missing mass. It is time to unravel how we first realized that something vital was missing from the starlight. In the 1930s, a Swiss astronomer named Fritz Zwicky gazed at a distant cluster of galaxies through his telescope. This cluster was like a swarm of sparkling islands floating in space. He measured how fast those galaxies were moving around each other and found something startling. They were moving so rapidly that by rights, the cluster should have scattered apart. There simply wasn't enough visible matter, not enough stars or gas that he could see, to hold the cluster together at those high speeds. It was as though an invisible glue were at work, an unseen mass whose gravity kept the galaxies bound together. Zwicky called this unseen mass dark matter, a poetic name for a cosmic mystery. His idea was met with curiosity, but also skepticism. The concept was so strange at the time that many in the scientific community did not know what to make of it. After all, no one had ever observed anything like this dark matter directly. For a while, the notion of an invisible substance lying hidden in the darkness remained on the fringes of astronomy, like a faint star at the edge of the sky, easily overlooked. Decades passed, and the mystery persisted quietly. Then, in the late 1960s and 1970s, new observations breathed life back into the puzzle. Imagine looking at a graceful spiral galaxy, a whirl of starlight shaped like a giant pinwheel. The stars near the center of the galaxy whirl around quickly due to the strong gravity of the dense core. Farther out, one would expect the stars at the edges to orbit more slowly, just as the outer planets in our solar system move more slowly around the sun. But to the surprise of astronomers, those outer stars were circling the galaxy at nearly the same speed as the inner ones. The galaxy's outskirts were not moving lazily at all. They were racing, as if pulled by the gravity of far more matter than anyone could see. This pattern turned out not to be unique to one galaxy, but was observed in many. Even our own Milky Way and the neighboring Andromeda galaxy exhibited this curious behavior in their outer regions. Stars at the fringes were moving fast when, by all rights, they should have been drifting slowly. It was as if an enormous hidden mass surrounded each galaxy, providing the extra gravitational pull. An astronomer named Vera Rubin was one of the pioneers who carefully measured these star velocities in spiral galaxies. Late at night, in quiet observatories, she studied the spectral fingerprints of starlight to gauge how fast those stars were rotating around their galactic centers. What she found defied expectations. The speed did not drop off in the outer regions. In fact, the rotation curves stayed flat, or even rose toward the edges. If only the visible stars and gas provided gravity, those outer stars should have drifted away into space. Clearly, something unseen was holding them in orbit, just as Zwicky's cluster had hinted decades before. This was a turning point. The evidence for missing mass could no longer be ignored. It was right there in the data, like a gentle but persistent echo from the darkness. Galaxies all across the universe seemed to be enveloped in cocoons of invisible matter that added to their gravity. Scientists began referring to this puzzle as the missing mass problem. The bright stars of the galaxies turned out to be only the sparkling foam on the crest of a deep, unseen ocean of matter. Beneath that glittering surface lay a vast sea of invisible mass that supported and held everything together. Bit by bit, scientists pieced together a startling revelation. In order for the universe to behave as it does, this dark matter must vastly outweigh the ordinary matter we can see. The stars, planets, and glowing gas, all the things that shine, turned out to be only a tiny fraction of what's out there. Estimates grew more precise over time, and today we believe that for every part of normal matter, there is about 5 times more dark matter lurking unseen. In other words, the majority of the matter in the cosmos is invisible, hiding in plain sight. Think about that for a moment. Most of the material that makes up the universe does not emit any light, not a glimmer. If we could somehow see this dark matter, the night sky would look very different. Perhaps the outlines of immense structures would glow faintly around galaxies and clusters. But dark matter is elusive. It neither glows nor casts a shadow in the traditional sense, because it interacts with light so faintly that, for all intents and purposes, light passes right through it. To our eyes and telescopes, it is truly dark. So how, then, do we know it's there at all? We know it by its gravity, by the way it tugs on things we can see. It is much like knowing the wind is present by watching leaves dance. You can't see the air itself, but you see what the air moves. In the quiet depths of space, dark matter's gravity makes stars and galaxies dance in ways we can measure. It holds galaxies together, and it gently pulls on light passing by from distant sources, bending it ever so slightly. This is how the universe tips us off to the presence of its invisible mass, through subtle gravitational whispers. At this point in our journey, the idea of dark matter was no longer just speculation. It had become a central piece of our understanding of the cosmos. The missing mass had been found, at least indirectly. Yet discovering that it exists is not the same as understanding what it is. That question remained unanswered and continues to intrigue and mystify scientists to this day. What is this dark matter made of? Is it some kind of exotic particle drifting through us this very moment? Why does it not shine or interact with ordinary matter except through gravity? The mystery of its nature is as deep and dark as the space between the stars. Though we cannot answer these questions yet, we do know something about what dark matter does. We know it is out there, surrounding galaxies and forming invisible structures that span the cosmos. To truly appreciate this unseen presence, let's venture further into a cosmic perspective. Now, let us drift outward into space, far from our own solar system and beyond the edge of our Milky Way. Imagine we are floating in the quiet cosmic ocean, looking back at our galaxy from a great distance. The Milky Way spreads out below us like a shimmering disk of stars, its spiral arms glowing softly in the dark. Hundreds of billions of stars knit together into a luminous tapestry, rotating slowly around the galactic center. It is a magnificent sight, yet what we see is only the beginning of the story. Surrounding that splendid spiral is something we cannot see with our eyes, but it is there nonetheless. Enveloping the galaxy is an enormous halo of dark matter, extending well beyond the farthest reaches of the starlight. This halo of the unseen is like a vast, transparent sphere that dwarfs the visible galaxy within it. If we could somehow make the dark matter visible, we would behold the Milky Way swaddled in a huge glowing aura of ghostly light. This halo contains much more mass than all the stars and gas in the galaxy combined, and its gentle gravity grips the galaxy, helping to keep those whirling stars in their orbits. It's a peaceful thought, in a way, an invisible cocoon holding our galaxy securely, cradling it through cosmic time. And our Milky Way is not unique in this. Every galaxy we know of appears to sit within such a halo of dark matter. Spiral galaxies, elliptical galaxies, even tiny dwarf galaxies are all embraced by these unseen halos. We discovered them only through their effects, the way stars move, the way galaxies stay bound. But in our minds, we can picture them, these vast halos, gently shining with a light that only gravity can produce. Now imagine we travel farther out, beyond a single galaxy, to gaze at the large-scale structure of the universe. We begin to see that galaxies are not isolated at all. They are arranged in a pattern, like glowing beads on invisible threads. Gigantic filaments of dark matter stretch across intergalactic space, forming a cosmic web that spans the universe. At the intersections of these filaments sit clusters of galaxies, bright nodes in a vast cosmic lattice, an enormous framework made mostly of dark matter. The dark matter in the filaments is itself invisible, but it tugs on anything with mass, drawing galaxies toward each other along these bridges. Our universe, as it turns out, has a hidden architecture, a scaffold woven from dark matter's gravity, upon which the luminous galaxies are assembled. These ideas are not mere fantasies. Astronomers, by observing galaxies and simulating cosmic evolution, uncovered this web-like structure. They realized that long ago, in the early universe, dark matter began to clump together under gravity, forming seeds and filaments. Ordinary matter, which can radiate heat and cool down, then fell into the gravitational embrace of those dark matter clumps and eventually formed the first stars and galaxies along the dark scaffolding. Without dark matter guiding the way, the cosmos might have developed very differently, perhaps with far fewer galaxies lighting up the darkness. In a sense, dark matter provided the framework for the universe to build upon. As we continue to float in this cosmic expanse, we might wonder how we can be so sure this unseen stuff is truly out there in these halos and filaments. One remarkable clue comes from a phenomenon called gravitational lensing, the bending of light by gravity. Massive objects, like galaxies and clusters, can act like lenses, warping the light of more distant galaxies behind them. When astronomers observe a massive cluster of galaxies, they sometimes see the distorted images of faraway galaxies in the background, stretched into arcs, or even smeared into rings of light. These beautiful distortions reveal that there's more mass in the cluster than we can account for with visible matter alone. It's as if the invisible halo itself is bending the light and betraying its presence. You might visualize this effect like looking through a curved piece of glass. The background scenery appears warped and reshaped. In the cosmos, the role of the glass is played by gravity. A galaxy cluster with a massive dark matter halo can bend light from objects behind it into surreal shapes. By carefully studying these patterns, scientists can map out the unseen mass. Time and again, these maps show large halos of dark matter enveloping clusters and even connecting between them, just as our theories predicted. In a very real sense, we have observed the silhouette of dark matter through these cosmic lenses. Not a direct picture, but a clear shadow cast by its gravity. Another dramatic piece of evidence for dark matter's presence came from observing colossal collisions in space. Imagine two immense clusters of galaxies, each one a swarm of hundreds of galaxies, accompanied by enormous clouds of hot gas and dark matter, hurtling into each other over billions of years. When they finally collide, the galaxies themselves mostly glide past one another, like two flocks of birds mingling briefly, because the distance between individual stars is so great. The hot gas in each cluster, however, does not slip by so easily. Those gas clouds collide, slow down, and heat up, glowing brightly in X-ray light at the center of the impact. But the dark matter, being nearly non-interactive, simply sails through the collision. It hardly even notices the encounter, passing by the colliding gas and stars like a ghost through fog. Astronomers observing such an event found something extraordinary. The main sources of gravity, as mapped by gravitational lensing of background light, had moved ahead of the collision, separating from where most of the visible matter, the hot gas, remained. In other words, the invisible mass was in a different place than the ordinary mass. We essentially watched the dark matter from each cluster drift past the crash, leaving the slowed gas behind. It was a cosmic demonstration of the unseen and the seen parts of the universe parting ways. This was like catching a ghost in the act. The normally invisible halos made their presence unmistakably known by behaving differently from regular matter. All these observations in the depths of space tell us that dark matter is real and deeply woven into the fabric of the cosmos. Yet even as we map where dark matter is, we are still left to ponder what it is. To answer that, scientists have turned to another front of discovery, one that takes place here on Earth. They are attempting to detect dark matter particles directly, to finally touch this shadow substance that has only been known by its influence. One approach is to listen for dark matter in the most silent places we can find. In laboratories, deep underground, shielded by layers of rock, scientists have set up extremely sensitive experiments. The depth and stone overhead protect these labs from cosmic rays and other interference, creating a quiet environment akin to a still pond undisturbed by rain. Inside, large detectors made of ultra-pure materials wait patiently. They might be vats of liquid noble gases or crystals chilled to near absolute zero. All the apparatus sits in darkness and stillness, watched over by instruments that can pick up the faintest of signals. The idea is that if a dark matter particle, which normally passes through matter without a trace, were to strike an atom in one of these detectors, it would jostle it ever so slightly. That tiny interaction could produce a small flash of light or a faint electrical signal. The scientists keep vigil for these subtle signs, much like anglers on a calm night watching the undisturbed surface of a lake for the slightest ripple. The experiments run quietly for months and years as researchers sift through the data for any whisper that might indicate a dark matter particle has finally revealed itself. So far, these direct searches have not yet caught the culprit. No definitive flash or telltale knock has announced the presence of dark matter in our detectors. The dark particles remain elusive, slipping through our instruments as silently as they move through space. There have been tantalizing hints here and there, but nothing confirmed with certainty. Still, scientists persist, refining their techniques and listening even more carefully, because the stakes are profound. Detecting a dark matter particle would open a new window onto this shadow universe, telling us exactly what this mysterious substance is made of. As we ponder this, think of how remarkable it is that even now, as you rest and listen, countless dark matter particles may be streaming through your body and through the earth itself, yet you feel nothing. They are like a gentle breeze we cannot feel or hear, present but imperceptible. We live our lives oblivious to this invisible rain of particles because they rarely interact with us at all. Only on cosmic scales do their effects become clear, influencing the motions of galaxies and the growth of structure in the universe. It's humbling to realize that we are submerged in this vast ocean of the unseen, our world moving through it as if through a mist that our senses cannot detect. Dark matter, this hidden mass, is a fundamental part of our universe. It has quietly shaped the heavens, governing the dance of galaxies and the architecture of the cosmic web. In doing so, it has also shaped our own existence. Without dark matter, the Milky Way might never have formed in a way that could nurture our sun and planet. And yet, for all its importance, it remains an enigma. Our journey so far has illuminated the presence of this darkness, but not its identity. It's as if we have traced the outline of a vast silhouette in the night, without yet seeing the face of the one who casts it. You might wonder, is this where the mystery ends? Have we now found all the missing pieces of the cosmic puzzle? Interestingly, the tale of the dark universe has another chapter, one that surprised scientists even more than the discovery of dark matter. As we looked out into the distance of space and time, observing exploding stars in far-off galaxies, we expected to find the expansion of the universe slowing down, tugged by the gravity of all the matter, both visible and dark. Instead, we found the expansion speeding up. The galaxies were drifting apart faster and faster as time went on, as if propelled by a repulsive force or a kind of energy embedded in space itself. This was the first hint of what we now call dark energy. It is a name for our ignorance, really, a placeholder for something we hardly understand. Dark energy appears to fill all of space like a uniform, gentle pressure, pushing galaxies apart over vast distances. Unlike dark matter, which pulls things together with gravity, dark energy has the opposite effect on the scale of the entire universe. It's as though the universe has two unseen ingredients, one acting as cosmic glue and another acting as a sort of cosmic spring, stretching the fabric of space wider and wider. Dark energy is even more elusive and mysterious than dark matter. We cannot bottle it up or detect it in a lab. We infer its existence from the motion of distant supernovae and subtle patterns in the light from the early universe. Yet, according to our best measurements, this dark energy accounts for nearly 70% of all the stuff in the universe when we convert mass and energy to the same scale. That means the lion's share of the cosmos is made of this enigmatic force driving the expansion, with dark matter being the next largest component, and ordinary matter, everything we know, from galaxies to planets to people, making up only a small remainder. Our journey will continue to explore this idea, to seek an understanding of dark energy's nature. But at this gentle moment, we can pause and reflect on how much has been revealed and how much remains a mystery. We have sailed among galaxies and felt the gravitational pull of invisible halos. We have marveled at a universe where much of its content is hidden in shadow. And we have learned that even this is not the whole story. For the darkness holds yet another secret in the form of dark energy. For now, let's simply rest in the wonder of it all. The night sky above, the ground beneath, and the vast universe beyond are connected in ways we are only beginning to grasp. The darkness that once seemed empty is filled with influence and meaning. Take a slow, deep breath and imagine the countless stars overhead, each with its own hidden halo, all floating in a boundless space that is quietly expanding. Feel the peace of that thought, a universe serenely unfolding its mysteries. When you are ready, we will continue our cosmic journey and delve into the mystery of dark energy, the shadowy force behind the universe's accelerating expansion. Until then, you may linger here as long as you like, under the gentle night sky of our story, comfortable and unhurried. The stars shine steadily, the unseen halos keep their watch, and the cosmos holds its secrets with patient grace. In this calm interlude, you are part of this grand universe, both the known and the unknown. And as you close your eyes, you can sense that even in darkness, you are cradled by the cosmos itself, wrapped in the soft glow of starlight and the quiet presence of all that remains unseen. In the silent darkness of space, gravity often hints at things we cannot see. Stars whirl around galaxy centers, and galaxies themselves dance in clusters with more haste than the visible matter can justify. These motions betray the gravitational pull of something hidden, as if an invisible mass is casting a shadow that we detect only by its influence. Astronomers have found that many cosmic movements and distortions cannot be explained by the gravity of luminous stars and gas alone. Instead, an unseen presence provides the extra gravity needed to hold galaxies and galaxy clusters together, revealing itself only through the subtle tug it exerts on visible objects. One of the clearest signs of this hidden influence appeared in the way galaxies rotate. In a spiral galaxy like our Milky Way, you would expect stars farther from the center to orbit more slowly, much like distant planets take longer to circle the sun. But in reality, the stars in the outer reaches of galaxies are moving just as fast as those near the core. Instead of slowing down, their speeds remain high and nearly constant, resulting in a flat rotation curve across the galaxy. This astonishing observation was first confirmed in the 1970s by astronomer Vera Rubin, who found that galaxies have far more gravity than the visible matter alone could provide. As Rubin analyzed galaxy after galaxy, a startling picture emerged. Each is enshrouded in an enormous halo of unseen mass. Calculations showed that this dark halo contains at least as much mass as all the stars in the galaxy, and in many cases, several times more. In fact, astronomers determined that as much as 90% of a galaxy's total mass could be hidden in this invisible halo. This meant that the bright portion of a galaxy is only a small fraction of its true mass, the rest being hidden in darkness. Without this hidden gravitating mass, the outer stars would not have enough pull to keep them in their orbits. They would simply drift off into space. Initially, many scientists found Rubin's findings hard to accept, but over time her results were confirmed again and again as more galaxies were studied. Astronomers came to realize that an invisible substance, soon named dark matter, provides the extra gravity, acting as a cosmic glue that holds each spinning galaxy intact. What began as a startling idea became a fundamental principle. Galaxies are mostly made of dark matter. Long before Rubin's discoveries, there had been hints of hidden mass on even larger scales. In 1933, astronomer Fritz Zwicky studied the Coma cluster, a large assembly of galaxies, and noticed something perplexing. The galaxies in this cluster were moving so rapidly that they should have flown apart, unless the cluster held far more mass than was visible. Zwicky calculated that the Coma cluster held about 400 times more mass than what could be seen, and he dubbed this unseen mass Dunkel Materie, German for dark matter. In his view, the cluster was filled with some kind of invisible material binding it together. At the time, his idea was largely overlooked, but it was a prescient clue to the shadowy matter that permeates the cosmos. In the decades since, galaxy clusters have provided further compelling evidence of dark matter's gravitational shadow. Observations show that clusters are filled not only with galaxies, but also with enormous clouds of hot gas that far outweigh all the stars. Yet even this gas, which can be as massive as the entire galaxy collection, is not enough to explain the cluster's gravity. The total pull holding a cluster together still exceeds what visible matter supplies, implying an even greater invisible mass is present. Without this dark matter, the galaxies and hot gas in clusters would not remain bound. They would drift apart over time. Instead, clusters stay intact, the visible matter held in the grip of a much larger, unseen mass. Another powerful way to detect the gravity of invisible matter is through gravitational lensing. According to Einstein's theory, a massive object like a galaxy cluster can warp space and bend the light from more distant galaxies behind it. Indeed, when astronomers observe a massive cluster, they often see faint background galaxies distorted into arcs of light by the cluster's intense gravity. By analyzing these warped images, astronomers can map the cluster's mass distribution and determine its total mass. The remarkable finding is that the gravity needed to produce the observed lensing is far greater than what the visible galaxies and gas alone can supply, meaning most of the cluster's mass must be invisible dark matter. One striking example of dark matter's presence is the Bullet cluster, a famous collision of two galaxy clusters that offered an extraordinary test. In this cosmic event, the cluster's clouds of hot gas, which contain most of the normal matter, slammed together and were slowed by the immense drag of the collision. The gas, heated to hundreds of millions of degrees, now glows in X-ray light and lingers near the impact site. The galaxies from each cluster, by contrast, flew past one another almost unimpeded. Crucially, the dark matter associated with each cluster also sped through the collision alongside the galaxies, instead of being slowed with the gas. In the Bullet cluster, astronomers could essentially see dark matter separating from normal matter by mapping the gravity after the collision. When they measured the gravitational lensing in the aftermath, they found that the bulk of the mass was offset from the hot gas clouds. The lensing revealed that most of the mass had moved ahead with the galaxies, rather than remaining with the gas left at the center. If there were no dark matter, the mass would have stayed with the visible gas. But in the Bullet cluster, the mass clearly went with the galaxies. This remarkable observation provides direct proof that dark matter is a real, distinct form of matter, dominating the cluster's mass. From the scale of individual galaxies to the realm of enormous clusters, gravity's shadow reveals that the majority of matter in the universe is dark and unseen. This dark matter forms giant halos around galaxies and clumps in great clouds within clusters, providing the gravitational glue that luminous matter alone cannot supply. It neither emits nor absorbs light, making it effectively invisible, but its gravity sculpts the cosmos. All the observational evidence so far points to a cosmos where this dark component far outweighs the ordinary matter. And the influence of dark matter stretches far beyond clusters, extending across the universe itself. Over cosmic time, dark matter's gravity guided the formation of structure on the grandest scales. It drew galaxies together into filaments and left vast voids between them, creating an immense cosmic web that spans billions of light years. To see how this invisible scaffolding shaped the cosmos, we now step back and look at the universe on its largest scales, where the pattern of the cosmic web emerges. Far beyond our galactic neighborhood, on the grandest scales, the universe reveals a hidden pattern. Galaxies are not scattered randomly through space. Instead, they trace out a vast, lace-like design, a cosmic web. In this web, galaxies collect in groups and clusters, and these clusters connect along unimaginably long filaments. Between the filaments lie immense voids where few galaxies dwell, giving the cosmos a structure akin to a sponge or a spider's web, with threads of matter and great empty spaces in between. Astronomers have mapped this large-scale structure and found that it indeed resembles a giant three-dimensional web. Clusters and superclusters of galaxies form the nodes, and slender filaments of galaxies stretch between them. In between are enormous bubble-like voids that contain hardly any galaxies at all. It is as if the galaxies were resting on the surfaces of empty bubbles, outlining the structure of invisible matter with their luminous glow. This cosmic web provides a sort of scaffolding that cradles all the matter in the universe. The discovery of the cosmic web unfolded over the late 20th century. In the 1980s, the first large surveys of galaxy positions revealed gigantic sheet-like structures and voids. In 1989, scientists led by Margaret Geller and John Huckra announced the Great Wall, an enormous wall of galaxies stretching roughly 500 million light-years across space. This was the first definite glimpse of a galaxy superstructure, confirming that galaxies form connected systems on scales far beyond clusters. Since then, other colossal structures have been identified, and the reality of the cosmic web has become unmistakable. Equally striking are the voids, the dark cells of the cosmic web's honeycomb. One famous example is the Boötes void, a tremendously large region about 330 million light-years in diameter that contains almost no galaxies. Where one would expect thousands of galaxies, astronomers found only a few dozen. Discoveries like the Boötes void drove home just how vast and empty some regions of the universe are, and how filamentary the distribution of matter must be on these scales. What creates this immense cosmic web? The answer is gravity, guided chiefly by dark matter. Long ago, in the early universe, matter was almost evenly spread out, but not perfectly. Tiny ripples in density, the seeds of structure, were present. Dark matter began to clump around those seeds, forming a gravitational scaffold, even while ordinary matter remained a hot gas. Over billions of years, the dark matter drew in the ordinary matter, funneling gas and galaxies into the growing filaments and clusters. In this way, dark matter laid down the invisible framework of the cosmic web, and galaxies later formed and lit up along this framework. The gravity of dark matter is the cosmic web's architect, pulling the visible universe into its intricate design. Today, advanced computer simulations allow cosmologists to recreate this process. When they simulate a universe filled with dark matter and let gravity work over billions of years, a filamentary cosmic web naturally emerges. The simulated galaxies line up along invisible dark matter filaments, gathering into clusters at the intersections, a striking match to what we observe in the real universe. These simulations bolster our confidence that we truly understand how crucial dark matter has been in sculpting cosmic structure. In fact, not only does dark matter permeate these filaments, but a substantial amount of the universe's ordinary matter is thought to reside there as well, dispersed as a thin, hot plasma that is very difficult to detect. Astronomers long suspected that this missing normal matter lurks in the vast spaces of the cosmic web, and recent observations have started to confirm it. By using distant flashes of radio waves called fast radio bursts and sensitive X-ray telescopes, scientists have detected a faint glow from diffuse gas tracing out intergalactic filaments. Even ordinary atoms, it appears, collect along the dark matter strands, filling in the cosmic web and completing the picture of where matter lies. Ongoing galaxy surveys continue to map the cosmic web in greater detail. Projects like the Sloan Digital Sky Survey have charted millions of galaxies, revealing ever larger patterns. Astronomers even discovered an even bigger structure, the Sloan Great Wall, which spans about 1.4 billion light-years, an expansive chain of galaxy clusters and filaments showcasing the immense scale of the web. Every survey confirms the same picture. On large scales, matter in the universe isn't uniform at all, but gathered into this beautiful, filamentous arrangement. By studying the cosmic web, scientists also glean insights into cosmic history and the cosmos's composition. The distribution of galaxies and voids holds clues about the initial fluctuations in the Big Bang and the amount of dark matter shaping structure. Even the influence of dark energy, the mysterious force accelerating the universe's expansion, can be probed by the way the cosmic web's growth has slowed over time. The cosmic web, in effect, is a record of how structure formed under the tug-of-war between gravity and expansion. Yet, to truly decipher the ingredients of the universe, to measure exactly how much dark matter and dark energy exist, we must look even further back, to the very infancy of the cosmos. There, in the cosmic microwave background, the faint afterglow of the Big Bang, lies a record of the universe's earliest moments. This primordial light acts as a cosmic fingerprint, one that reveals the full recipe of the cosmos. It will show us the proportions of dark matter, dark energy, and ordinary matter, guiding us onward in our journey through the shadow universe. Every direction we look in space, there is a faint glow of microwaves, a uniform whisper of light that fills the cosmos. This is the cosmic microwave background, often called the afterglow of the Big Bang. It is the oldest light we can see, a fossil radiation dating back to a time when the universe was newborn. To our instruments, it appears as an almost perfectly even background at about 2.7 degrees above absolute zero, gently bathing the entire sky. The existence of this cosmic background glow was first discovered by accident in the mid-1960s. Two American astronomers, Arno Penzias and Robert Wilson, were using a large horn-shaped radio antenna in New Jersey when they encountered a persistent, mysterious hiss of microwave noise coming from all directions. They checked and rechecked their equipment, even shooing pigeons from the antenna to clear out any interference. But the noise remained. Eventually, they realized they had detected something profound: the cosmic microwave background radiation, the faint remnant light from the Big Bang itself. This discovery, made in 1965, provided the first direct evidence that the early universe was once hot, dense, and filled with brilliant light. In its infancy, about 380,000 years after the Big Bang, The universe was a hot, opaque fog of plasma, a soup of electrons, protons, and photons at about 2700 Dugard. As the universe expanded and cooled, those electrons and protons combined to form neutral hydrogen atoms. Suddenly, the fog cleared. The blinding light was set free to travel through space. That light has been journeying across the cosmos ever since, growing fainter and cooler as the universe expands. Today, it has cooled to a microwave glow just 2.7 degrees above absolute zero. This is the cosmic microwave background, CMB, the very same all-sky signal that Penzias and Wilson detected as a gentle hiss of microwaves. Remarkably, the CMB is almost uniform wherever we look, but not entirely. Spacecraft and satellites have measured tiny variations in its temperature, only about 1 part in 100,000. These slight hot and cold patches appear as a speckled pattern on the otherwise even background. Those tiny temperature fluctuations correspond to regions of slightly different density in the early universe. They are the imprint of primordial sound waves and clumps, essentially the seeds of all future structure. In the faint mottling of the CMB, we are seeing the infant universe's landscape, the denser spots that would grow into galaxies and clusters, and the less dense spots that would become vast cosmic voids. By analyzing this delicate patchwork of CMB fluctuations, scientists can deduce the contents and evolution of the universe from its birth to the present. The size, distribution, and strength of the hot and cold spots act like a cosmic fingerprint, encoding information about the universe's composition. Cosmologists have painstakingly measured this pattern with missions like COBE, WMAP, and most recently the Planck satellite, which mapped the CMB across the entire sky in extraordinary detail. The results tell a clear story. To reproduce the observed CMB patterns, the universe must contain a certain mix of ingredients. That mix, as revealed by the CMB, is startling. Only about 5% of the universe's mass energy is the ordinary matter that makes up stars, planets, and us. About 27% is dark matter, the invisible mass that sculpts galaxies and clusters. And nearly 68% is dark energy, a mysterious form of energy driving the acceleration of the universe's expansion. These proportions, derived from the CMB and other data, paint a precise picture of a universe dominated by dark components. The luminous matter we see is only a tiny fraction of what's out there. The CMB measurements not only quantify dark matter and dark energy, they also affirm that dark matter is truly required. Alternative ideas that tried to explain cosmic structure without dark matter fall short in the face of the CMB's detailed pattern. The specific ratios of the CMB's peaks and troughs, essentially the sizes of the spots, can only be explained if most matter is the unseen dark matter rather than normal atoms. In this way, the CMB provides an independent and resounding confirmation of dark matter's existence. Likewise, the flat overall geometry of the universe evident in the CMB implies that the total energy density is very close to the critical value of a flat cosmos. When ordinary and dark matter are accounted for, this leaves room for a major additional component: dark energy. At the same time, in 1998, distant supernova explosions were observed to be fainter than expected, indicating that cosmic expansion is accelerating. Together, the CMB and supernova evidence cemented the idea that a dark energy now dominates the universe's fate. All these discoveries have coalesced into a standard cosmological model, often called lambda CDM, LCDM. This model, with roughly 5% normal matter, 27% cold dark matter, and 68% dark energy, explains a vast array of observations, from galaxy clustering to the CMB itself. When the Planck satellite released its high-precision map of the CMB, it provided spectacular confirmation of this simple model. The Planck data allowed scientists to refine the cosmic recipe to unprecedented accuracy, and the fit to the lambda CDM model was nearly perfect. And yet, even as we celebrate this elegant cosmic picture, profound mysteries remain. We can now state how much dark matter and dark energy exist, but we still do not know what they actually are. Dark matter behaves like an elusive particle, or family of particles, that so far has evaded direct detection. Dark energy seems to act like a property of space itself, a smooth energy field causing cosmic expansion to speed up, but its true nature is completely unknown. Answering these profound questions is the next great frontier of cosmic exploration. In the next part of our journey, we will follow the scientists on the cutting edge, from deep underground detectors hunting for dark matter particles to space observatories probing dark energy's effects, as the search for the shadow universe's secrets continues. Deep beneath the Earth, in a laboratory carved out of ancient rock, a strange experiment is underway. Down here, shielded by hundreds of meters of rock, the usual rain of cosmic rays from space is all but absent. Apart from the faint hum of equipment, there is only silence. You can almost hear your own heartbeat in the still air. In the stillness and darkness, large tanks filled with crystal clear liquid lie waiting. They wait for a whisper from the dark, a momentary flicker of light, or a tiny jolt of energy that could be the sign of a passing dark matter particle. Shielded by mountains or mine shafts above, these experiments are designed to escape the noise of the everyday world and listen for one of the rarest events in the universe. Here, far from the starlight and cosmic rays, scientists have created one of the quietest places on Earth, all in hopes of catching the faintest touch of the invisible. The principle behind these experiments is simple in concept, but challenging in practice. If a dark matter particle flying through space happens to slam into an atom inside the detector, it will jostle that atom ever so slightly. That tiny disturbance might produce a faint flash of light or a minute electrical signal. Sensitive photodetectors and electronics surrounding the tank stand guard, ready to amplify and record even the most subtle of these events. The hope is that amid the stillness, one of these instruments will catch a telltale wink, the brief spark indicating that a dark matter particle has finally made itself known by striking ordinary matter. In one such experiment, a large tank filled with liquid xenon is monitored by an array of ultra-sensitive light detectors. The detector is buried under a mountain, encased in layers of shielding to fend off stray particles and radiation. It sits in quiet darkness, waiting. If a dark matter particle strikes a xenon atom, it will produce a faint flash of light and a tiny cascade of electrons. Dozens of photomultiplier tubes around the tank can amplify that feeble glow, allowing scientists to record the event. Everything, from the purity of the liquid xenon to the radioactivity of the detector materials, is painstakingly controlled. The goal is to reduce background noise to nearly zero, so that a true dark matter interaction would unmistakably stand out. Such an encounter would be exceedingly rare. To catch one collision, these detectors often must watch for months or even years on end, sifting through the silence. During all that time, any stray signal from the environment could cloud the search. Cosmic rays from space, natural radioactivity from the rocks, Even a slight warmth or vibration can produce tiny flashes or noise that might masquerade as a false hint of dark matter. That is why the labs are hidden deep underground and built with ultra-clean materials, to block out as much interference as possible. Every possible source of noise is minimized, so that if a lone dark matter particle ever does bump an atom in the detector, it will stand out like a clear whisper in an otherwise silent night. After all this patience and watchfulness, what have these experiments seen? So far, the answer is mostly a profound silence. Occasionally, a sensor flickers or a detector blips, but such events, upon careful scrutiny, turn out to be ordinary particles or electronic noise, rather than a telltale dark matter interaction. As each year passes, without a confirmed sighting, the scientists glean something nonetheless. They learn what dark matter is not. Each non-detection sets new limits on how often dark matter can collide with normal matter, and how heavy or light these particles might be. Bit by bit, the range of possibilities for dark matter's properties is narrowed. Paradoxically, even the absence of a signal is teaching us, whispering that if dark matter is out there, it is even more ghostly and shy than we had hoped. On occasion, a detector does see an intriguing signal, a handful of events that look like they might be something new. Such moments send a thrill through the scientific community. Could this be the first direct glimpse of dark matter? But extraordinary claims require extraordinary evidence. Each potential hint is met with deep scrutiny and attempts at independent verification. So far, these tantalizing flashes have not held up under examination. Either they were statistical flukes or subtle interference that wasn't initially recognized. It's a sobering reminder that nature guards her secrets well, and scientists must be vigilant to separate a true whisper of dark matter from the chatter of more ordinary phenomena. Every so often, tantalizing hints appear that tempt scientists into thinking a discovery might be close. In one laboratory, deep under a mountain in Italy, an experiment has for years reported a strange pattern in its data, a gentle rise and fall in its detection rate that repeats every year. Each summer, the detector registers slightly more tiny flashes than it does each winter. One interpretation is that as the Earth orbits the Sun, it is ploughing through the densest part of our galaxy's dark matter halo in June, and through a thinner part of it in December, causing a yearly wave in the number of particle hits. It was an exciting hint, potentially the first direct sign of dark matter's presence. However, other experiments elsewhere in the world have not detected the same seasonal signal. The claim remains hotly debated and unconfirmed to this day, a faint whisper that could be a genuine clue or simply a coincidental fluctuation in the data. Episodes like this keep scientists both hopeful and cautious. They remind us that nature's secrets often require repeated verification and a healthy dose of skepticism before we can proclaim a discovery. Meanwhile, other scientists have turned to colossal machines in the quest for dark matter. Underneath the border of Switzerland and France runs a 27-kilometre circular tunnel housing the Large Hadron Collider, the world's most powerful particle smasher. Here, proton beams are accelerated to nearly the speed of light and then collided head-on. The idea is that in the energy of these immense collisions, new particles might emerge, possibly including dark matter particles, if nature allows it. Should a dark matter particle be created, it would escape the detectors without a trace, disappearing like a ghost. However, it would leave behind a signature in the form of missing energy, as something unseen carries away a portion of the collision's energy and momentum. To find such clues, physicists sift through vast amounts of data from these collisions, looking for events where something seems to be missing, as if an invisible particle carried away a chunk of energy. Despite years of running and countless proton collisions, no clear dark matter signal has appeared yet in the LHC data. One leading hypothesis, called supersymmetry, predicted a new family of particles, and the lightest of these could have been an ideal dark matter candidate. The LHC has searched for such particles diligently, but so far, none have been seen, adding to the mystery. This null result has also taught us something. If dark matter particles can be forged in collisions, they either are extremely hard to produce, or they require energies higher than we have so far achieved. Even so, the search at the collider goes on. With each upgrade and each new batch of data, scientists remain watchful for any subtle anomaly, any faint hint that a dark particle might have been born and slipped away undetected in their machines. Researchers know that even a null result is valuable information, guiding them toward new directions and helping refine their theories for the next round of experiments. Some dark matter hunters have turned their attention to the sky. If dark matter particles annihilate each other or decay, they could produce a faint drizzle of high-energy radiation or exotic particles. Astronomers have searched the cosmos for these subtle clues, pointing telescopes at the centers of galaxies and at small satellite galaxies rich in dark matter, scanning for any glimmer that can't be explained by known astrophysical phenomena. They hope to spot a pattern or an excess of energy that stands out from the cosmic background, a fingerprint of dark matter in the heavens. One intriguing observation came from a space telescope that detected an unexpected glow of gamma rays at the center of our Milky Way. For a while, some scientists speculated that this could be the long-sought signal of dark matter particles annihilating each other, releasing energy in the form of gamma radiation. However, the galactic center is an extremely busy region, packed with pulsars, black holes, and stellar explosions, all of which can produce gamma rays. After extensive study, it turned out that this mysterious glow could be explained by those conventional sources rather than by dark matter. The tantalizing signal was likely just an ordinary whisper from known astrophysical objects, not the secret language of dark matter, after all. Another curious signal came from a detector aboard the International Space Station, which observed more high-energy positrons, the antimatter version of electrons, than expected. This anomaly raised eyebrows, because dark matter annihilations could potentially produce an excess of positrons. For a time, it seemed like a potential clue. Perhaps dark matter particles were colliding and turning into these positrons. But just as with the gamma-ray glow, other explanations soon came to light. Fast-spinning neutron stars called pulsars, or other cosmic accelerators, could also be responsible for the extra positrons, and the evidence wasn't clear-cut enough to claim a dark matter discovery. Even neutrinos, nearly invisible particles, have been brought into the search. Gigantic detectors buried in ice and deep mines watch for an unexpected surplus of neutrinos from the Sun or Earth's core, which could signal dark matter annihilations. But so far, they have seen only the expected background. These cosmic searches show how nature often keeps us guessing. Signals that once looked like possible dark matter fingerprints often fade back into the tapestry of ordinary astrophysical phenomena after deeper scrutiny. Yet astronomers continue to watch the skies with ever more sensitive instruments. They remain hopeful that someday a discrepancy will stand out unmistakably, a clear sign that against the cosmic noise, we have finally heard dark matter's voice. Not all dark matter candidates are heavy. Some could be almost ghostly light. One such candidate is called the axion, a hypothetical particle so lightweight it might act less like a particle and more like a field, gently waving through space. If axions exist, in the presence of a powerful magnetic field, they could sometimes morph into faint radio waves. To search for this, scientists have built devices that resemble extremely sensitive radio receivers placed inside strong magnets. They carefully tune these instruments across different frequencies, essentially listening for a telltale tone that an axion might produce by turning into a photon, a particle of light, inside the device. It is an extraordinarily challenging search, akin to trying to hear a single specific note in a symphony of noise. So far, these axion radio experiments have not detected any clear signal either, but they are steadily sweeping through the possible frequencies, narrowing down where an axion's whisper might be hiding. This approach is another example of the creativity scientists bring to the hunt. Rather than waiting for dark matter to bump into something, they are actively listening for the soft hum of an entirely new realm of physics. After years of looking under every proverbial rock, the lack of a dark matter signal has forced scientists to rethink their assumptions. Maybe the dark matter particle is even more elusive than we imagined, perhaps far lighter, far heavier, or interacting more weakly with normal matter than our initial theories guessed. The early favourite candidate, the WIMP, has managed to slip through all our traps so far. If such WIMPs exist, they are hiding exceedingly well, and that has led researchers to broaden their scope and consider other possibilities. New ideas have gained momentum. Some scientists now speculate that dark matter could be made of ultralight particles, like axions. Or perhaps there isn't just one dark matter particle at all, but an entire hidden family of particles with their own secret forces. With each experimental dead end, theorists refine their models and dream up alternative scenarios, ensuring that the pursuit continues in new directions. It's a bit like chasing a shape-shifting shadow. Every time you think you've pinned it down, it changes form or slips into a new hiding spot, prompting fresh strategies to keep up the chase. For the scientists involved, the hunt for dark matter is a test of perseverance and passion. It requires a special kind of patience, the willingness to spend years, even decades, chasing a particle that may only rarely, if ever, reveal itself. There are inevitable moments of frustration, when a long-anticipated experiment yields no signal, or when a tantalizing hint dissolves under closer examination. Yet these researchers remain undeterred, fueled by a deep sense of purpose. They are driven by a profound curiosity, the urge to understand the universe at its most fundamental level, and by the hope of contributing to a truly groundbreaking discovery. These experiments involve global collaborations, hundreds of scientists joining forces, all believing that the prize is worth the struggle. Veteran researchers mentor younger colleagues, passing on hard-earned wisdom, while fresh perspectives and new technologies keep the effort evolving. The quest has become multi-generational, a relay race in which each new team carries the torch forward. It stands as a testament to human determination that, with no guarantee of success, the search continues, fueled by wonder and the possibility of uncovering one of nature's deepest secrets. And so, after all the experiments, observations, and theoretical pondering, dark matter remains elusive. We have mapped its vast footprints in the cosmos and felt its gravitational tug, but we have yet to directly touch it or see it in our detectors. It still lurks in the shadows, a fundamental ingredient of the universe that we know is there, but do not yet truly understand. This enduring mystery humbles us, reminding us how much of the cosmos remains unexplored and unknown. Yet astonishingly, dark matter is only part of the cosmic puzzle. Even as we struggle to illuminate this invisible mass, an even stranger phenomenon dominates the universe. It makes up most of the cosmos and is driving space itself to expand faster and faster. We call this force dark energy, and it may be an even deeper mystery than dark matter. Our journey through the shadow universe is far from over. Having chased one great unknown, we now find ourselves drawn to the next, as the cosmos continues to whisper its secrets, beckoning us onward. In the wake of dark matter's discovery, a profound question loomed. Just how heavy is the universe? To truly grasp the cosmos, scientists realized they needed to weigh it as a whole. Of course, we can't place the universe on a scale, but we can deduce its weight by measuring the density of everything it contains. The answer would reveal the cosmos's ultimate fate, whether space will expand forever or eventually fall back in on itself under gravity's pull. For much of the 20th century, astronomers debated the universe's fate. Would expansion slow to a stop and reverse into a big crunch? Or would it continue endlessly, letting galaxies drift apart into eternal night? Gravity fights against the initial impulse of the Big Bang, trying to tug everything back together. If the cosmos holds enough mass, gravity's pull will eventually triumph and halt the expansion. If there's too little mass, the expansion will never stop. There is a tipping point between these destinies, defined by what scientists call the critical density, the precise average density of matter and energy needed to balance on the knife edge between collapse and eternal expansion. How much matter is that exactly? The critical density turns out to be extremely small by everyday standards, only on the order of a few atoms worth of mass per cubic meter of space. Imagine an entire living room with just a handful of hydrogen atoms floating in it. That's roughly the density needed to eventually halt cosmic expansion. Space is remarkably empty, so achieving even this whisper of density across the vastness of the universe is no simple thing. For gravity to win in the end, the cosmos must average at least this much mass everywhere. If the actual density falls below that threshold, the universe is destined to expand without end. Early measurements of the universe's density delivered a surprise. All the stars, galaxies, and glowing gas, essentially all the visible matter, added up to only a tiny fraction of the critical density. By tallying up the light from galaxies and estimating their mass, astronomers found that normal matter contributes perhaps only a few % of the required density. In other words, the brilliant galaxies we see through telescopes, the grand spiral arms and shining clusters, are practically lightweight in cosmic terms. There simply isn't enough normal matter out there, by itself, to ever bring the expansion to a halt. Then came the realization that most of the universe's matter is dark. Over decades, evidence grew that galaxies and clusters sit in massive cocoons of invisible material. This dark matter doesn't shine or interact with light, yet its gravity betrays its presence by tugging on stars and bending the path of light itself. By the late 20th century, astronomers had become convinced that this unseen mass vastly outweighs all the normal matter in the cosmos. Astronomers estimated that dark matter is roughly 5 times more abundant than ordinary matter. Including this dark component, the universe's total mass density rose to perhaps 20 or 30% of the critical level. It was a tremendous boost compared to the paltry contribution from visible matter alone. But even 1/3 of the needed density was not enough. The cosmos still appeared too underweight to ever stop expanding under its own gravity. Unless there was some unknown source of additional mass energy, these findings implied the universe would not recollapse. With only about 1/3 of the required density, gravity's grip seemed too weak to ever stop the expansion. Many cosmologists began to accept that we live in an open universe, one that will expand forever, gradually thinning out over time. It was a wistful conclusion, a future where galaxies drift ever farther apart, their light slowly fading. Yet not everyone was convinced this was the final answer. a deep puzzle remained. Some theories hinted that the universe might be missing something, an invisible ingredient that had yet to be discovered. Intriguingly, some theorists saw hints that the underweight universe picture might not be the whole story. The leading cosmological theory of the day, called inflation, predicted that space should be flat, meaning the total energy density of the universe equals the critical density exactly. If all the matter, even including dark matter, added up to only about 30% of that, the remaining 70% had to come from something else. This realization suggested that a major component of the cosmos could still be missing. It sounded like science fiction. Could empty space itself hide a form of energy that eludes direct detection? Some scientists proposed that the vacuum might indeed harbor a mysterious energy, quietly adding weight to the universe. If such an effect were real, it could account for the missing 70% and finally bring the cosmos up to full critical density. Through the early 1990s, this idea remained a speculative whisper on the margins of cosmology, intriguing but awaiting any hint of observational evidence. Astronomers devised a plan. Rather than summing up mass directly, they would measure the deceleration of cosmic expansion as a way to weigh the universe. The idea was simple in principle. Gravity from matter should be slowing the expansion over time. If the universe was heavy with matter, it would have expanded faster in the past and decelerated significantly as time went on. If the universe had little matter, the expansion would have hardly slowed at all. By comparing the expansion rate at different epochs, effectively taking a cosmic speedometer reading across time, scientists hope to gauge the total amount of gravitating mass in the cosmos. To execute this plan, they needed cosmic mileposts bright enough to be seen across the vastness of space and with known true luminosity. Type Ia supernovae were the perfect candidates. These are exploding stars that flare with extraordinary, almost uniform brightness, serving as reliable beacons in distant galaxies. Because their intrinsic brilliance is nearly the same each time, astronomers can tell how far away a Type Ia supernova is by how dim it appears from Earth, like knowing the wattage of a light bulb and inferring its distance from its faintness. By measuring the distances of far-flung supernovae and how much their light had been stretched by cosmic expansion, researchers could reconstruct a history of the cosmic expansion rate. It was an ambitious plan that only became feasible in the late 20th century. Finding these supernovae is like catching distant flickers in the dark. They are rare and fade quickly. But advances in technology, from sensitive digital detectors to ever more powerful telescopes, enabled astronomers to systematically scan distant galaxies for the telltale glow of an exploding star. By the mid-1990s, international teams were racing to observe as many of these supernovae as possible, all eager to measure how much the universe's expansion had slowed over time under the pull of gravity. Everyone expected to see a clear slowing effect, a gentle deceleration caused by all the cosmic mass dragging on the expansion. The big question was whether that slowdown would be just enough to someday halt and reverse the expansion, or too slight, guaranteeing that expansion never ends. Either scenario would teach us more about the universe's fate. But when the data finally came in at the end of the decade, it defied all expectations. The universe, it turned out, was doing something no one had predicted. The results of the supernova surveys were staggering. Instead of slowing down, as everyone had expected, the expansion of the universe was actually speeding up. The distant supernovae appeared fainter than they should have been in a decelerating cosmos. They were farther away than anticipated, as if the space between us had stretched more than our models predicted. In plain terms, the universe wasn't putting on the brakes at all. It was hitting the accelerator. This was the opposite of what gravity alone would do, a discovery so radical that astronomers could hardly believe it at first. For a while, doubt hung in the air. The astronomers who found the unexpected result questioned everything about their analysis. Could the supernovae have been dimmed by dust, making them look more distant than they truly were? Could those distant explosions have inherently different properties, fooling the estimates? The teams painstakingly checked and rechecked their data, even looking for alternative explanations. But no matter how they sliced it, the conclusion held. The expansion of the universe was accelerating, not decelerating. And remarkably, two independent teams of researchers, working separately, had arrived at this baffling result in tandem. It was no fluke. It was the universe's real behavior on display. A sense of wonder and shock spread through the scientific community. It was as if we had tossed a ball into the air expecting it to slow and fall back, only to watch it shoot upward faster and faster. Gravity, the force that should have been reigning in the expansion, seemed to be overruled on cosmic scales by something entirely new. The universe, against all intuition, was not being slowed by its own mass. Instead, it was being pushed outward by a mysterious agent. This completely upended our understanding of the cosmos. Very quickly, scientists gave this unknown force a name: dark energy. The term dark signified not that it was literally dark, but that its nature was completely obscure to us. Just as dark matter is dark because we cannot see it or directly detect it, yet we know it's there from gravity, dark energy was an unseen influence making itself known through the acceleration of cosmic expansion. In effect, it behaved like a kind of anti-gravity, a repulsive property of space that was driving galaxies apart at ever-increasing speeds. Here was a phenomenon entirely unlike anything in the physics of planets, stars, or galaxies, a new feature of the universe on the grandest scale. In the midst of this revelation, an old idea resurfaced. In 1917, Albert Einstein had introduced a term in his equations of gravity called the cosmological constant. Essentially, a fixed energy woven into the fabric of space that acted like a repulsive force. He originally imagined it to counteract gravity and keep the universe static. Later, when Edwin Hubble discovered that the universe was expanding, Einstein discarded the cosmological constant, reportedly calling it his biggest blunder. But now, the accelerating universe suggested that Einstein's idea might not have been a blunder at all. Instead, it appeared to be a prescient glimpse of reality. In essence, a form of energy permeating the vacuum, just as Einstein once envisioned, seemed to be revealing itself. The effect driving the cosmic acceleration looked very much like a cosmological constant, a small, persistent energy embedded in empty space that pushes everything apart. As the reality of cosmic acceleration sank in, further evidence quickly followed. In the early 2000s, precision measurements of the cosmic microwave background, the faint afterglow of the Big Bang, revealed that the universe's geometry is flat. In a flat universe, the total energy density of the cosmos is exactly the critical value required to balance gravity. This finding offered a vital clue about the cosmic inventory. Yet astronomers already knew that all the matter, both normal atoms and dark matter, contributed only about 30% of that critical density. Something else had to make up the remaining 70%. That something was exactly in line with what the supernova studies had pointed to. Sure enough, detailed analyses of the CMB and the large-scale distribution of galaxies confirmed the need for a mysterious energy comprising roughly 70% of the universe. Matter made up the other 30%. Independent lines of evidence were thus converging on the same astonishing conclusion. The vast majority of the universe is dark energy. The cosmic bookkeeping was now fundamentally altered. Ordinary matter, the atoms that make up stars, planets, and us, turned out to be a mere trace of the cosmic ledger, on the order of only 5%. Dark matter, the unseen mass holding galaxies together, accounted for roughly 25%. And the rest, about 70%, was this newly recognized dark energy dominating the universe. The long quest to weigh the universe had led to an answer both elegant and unsettling. The universe is exactly balanced on the knife edge of critical density, as many theorists expected, but most of that balance comes from a form of energy we barely understand. We had finally weighed the cosmos, only to find that nearly all of its weight lies in shadows. Another realization dawned from the data. The dominance of dark energy is a relatively recent development in cosmic history. For billions of years after the Big Bang, the universe's expansion was gradually slowing down under the pull of matter's gravity. Galaxies were tugging on each other, and the expansion, while still continuing, was decelerating. But as the universe expanded and matter became more thinly spread, the effect of dark energy grew in comparison. Roughly 5 billion years ago, this repulsive energy overtook gravity as the dominant influence. Since then, the expansion has been speeding up. We find ourselves living in an epoch when dark energy rules the cosmos, causing space to stretch faster with each passing eon. For cosmologists, discovering dark energy was both a triumph and a humbling jolt. It showed that even at the turn of the 21st century, just when we thought we had the cosmos figured out, nature could still blindside us with a fundamental surprise. This revelation was so momentous that it earned the discoverers a Nobel Prize in 2011, among other honors. Yet beyond the accolades, a deep mystery remained. We now knew what the universe was doing, accelerating, but we did not know why. Giving it a name, dark energy, didn't explain it. It only underscored our ignorance. The real question loomed large. What exactly is this dark energy that so dominates the cosmos? And what does its existence mean for the future of the universe? The phrase energy of emptiness might sound like an oxymoron, but modern physics tells us that even empty space seethes with activity. According to quantum theory, the vacuum is not truly nothing. It's filled with virtual particles flickering in and out of existence and fields that never entirely vanish. These quantum fluctuations imbue empty space with a baseline energy. This vacuum energy is a prime suspect for what dark energy could be. If every bit of empty space has an inherent energy, then as the universe expands and creates more space, the total energy-driving expansion would increase, causing an acceleration. In essence, the idea is that empty space itself provides a kind of constant push on the universe. However, there's a deep conundrum here. When physicists calculate the expected vacuum energy from quantum theory, the result is astronomically high, far, far larger than what would produce the gentle cosmic acceleration we observe. In fact, the predicted vacuum energy density overshoots the observed dark energy density by an astonishing factor of about 10 or 120, a 1 followed by 120 zeros. It's arguably the biggest mismatch between theory and observation ever found. In simpler terms, if our current physics is correct, empty space should be bubbling over with energy. The universe's expansion would be absurdly fast. Clearly, that's not what we see. It appears that somehow, almost all of that vacuum energy cancels out, or is otherwise unexpressed, leaving behind only a tiny leftover push that we perceive as dark energy. Why this cancellation happens, why the vacuum energy is so incredibly small, yet not exactly zero, is a profound mystery at the heart of modern physics. This puzzle, often called the cosmological constant problem, has led scientists to consider some radical ideas. One suggestion invokes the anthropic principle. It posits that we observe an extraordinarily small vacuum energy, because if it were much larger, the universe would have expanded too rapidly for galaxies, stars, or life to form. In such a hostile cosmos, there would be no observers like us around to notice any dark energy at all. In a broader multiverse scenario, some physicists imagine there could be countless universes, each with different vacuum energy values. We naturally find ourselves in one of the universes where the vacuum energy is compatible with the existence of galaxies and life. This line of reasoning is speculative and not a testable scientific explanation, but it underscores just how puzzling dark energy's tiny value appears to be. It's almost as if the universe's parameters were delicately tuned to permit our existence, a notion that, while thought-provoking, continues to spark debate and philosophical reflection. While a constant vacuum energy, Einstein's cosmological constant, is the simplest explanation for dark energy, it's not the only idea on the table. Some researchers suspect dark energy might be more dynamic, perhaps a new field that evolves over time, nicknamed quintessence, after the ancient fifth element. Quintessence would be a diffuse energy field filling space that changes slowly as the universe expands. Unlike a true constant, its strength or pressure could vary, meaning the rate of cosmic acceleration might itself change over the eons. If dark energy is quintessence, the future could hold some surprises. The acceleration of the universe might continue to increase, or perhaps eventually taper off if the field weakens or decays. At present, though, all observations are consistent with dark energy acting like an unchanging vacuum energy. Thus far, it behaves eerily like a true cosmological constant. Still, scientists are keeping watch for any subtle clues that dark energy's strength might be shifting with time, since even a small deviation could reveal new physics at work. The ultimate fate of the universe hinges on the nature of this dark energy. If it truly is a constant vacuum energy, then the expansion will keep accelerating indefinitely. Distant galaxies will recede faster and faster until, in the far future, they vanish from our observable universe. Our night sky will grow emptier as stars and galaxies beyond our local group disappear from view over tens of billions of years. Trillions of years hence, nearly all stars will burn out, and the universe will fade into a cold, dark expanse, a scenario often called the Big Freeze. On the other hand, if dark energy somehow grows stronger over time, an extreme scenario sometimes called phantom energy, it could lead to a far more violent end, the Big Rip. In that hypothetical case, billions of years from now, the repulsive force would become so overpowering that it tears apart galaxies, then stars, and eventually atoms themselves, shredding the fabric of the cosmos. Conversely, it's also possible, though not supported by current evidence, that dark energy could someday weaken or even vanish, allowing gravity to gradually halt and reverse the expansion in a distant Big Crunch. At the moment, evidence leans toward an endless acceleration, but these speculative scenarios highlight how much remains unknown. Another line of inquiry asks whether dark energy is truly a new substance, or if it signals a flaw in our understanding of gravity itself. Einstein's theory of general relativity has passed every experimental test in the solar system and even on galactic scales, but on the scale of the entire universe, could gravity behave a bit differently? Some physicists have explored modified gravity models in which the equations governing cosmic expansion are tweaked, producing acceleration without any mysterious energy. Ideas range from subtle adjustments to gravity's behavior over vast distances to theories involving unseen extra dimensions that might influence cosmic expansion. Such concepts are intriguing, but they face the challenge of fitting all the precise observations we already have. So far, none of these alternate gravity theories has convincingly replaced the simple explanation of dark energy, and they're also difficult to test directly. Nonetheless, the willingness to question even gravity itself highlights the depths of the dark energy mystery. When confronted with something so unexpected, scientists are prepared to revisit even the fundamentals of physics in search of answers. On the observational front, scientists are gathering ever more data to pin down dark energy's properties. Dedicated surveys are mapping millions of galaxies to see how cosmic expansion has progressed over time, searching for subtle shifts that might reveal whether dark energy is truly constant or changing. Space missions like the European Space Agency's new Euclid telescope and NASA's upcoming Nancy Grace Roman Space Telescope are designed to measure cosmic expansion with exquisite precision, using distant supernovae and the clustering of galaxies as cosmic yardsticks to gauge the universe's growth. By observing how cosmic structures, such as galaxy clusters and enormous voids, have grown under the competing influences of gravity and dark energy, researchers hope to discern any fingerprints of new physics. Each new dataset acts as a report card on dark energy's behavior. So far, dark energy continues to earn top marks for imitating a classic cosmological constant. No deviations have been spotted. But the tests are still ongoing and will only become more sensitive in the coming years. So if dark energy is hiding any secrets, astronomers are determined to uncover them. Meanwhile, back on Earth, efforts are also underway to illuminate the other side of the dark cosmos, dark matter. In deep underground laboratories, physicists have built ultra-sensitive detectors, hoping to catch the faintest whisper of dark matter particles interacting with ordinary matter. At particle accelerators and in powerful observatories, researchers are searching for any hint of what this invisible mass might be. Together, the twin mysteries of dark matter and dark energy stand at the forefront of modern astronomy and physics. Cracking these secrets will require innovative technology and perhaps a radical shift in our understanding of fundamental physics. Each experiment and observation brings us one step closer to shedding light on this shadow universe. As we continue this journey, we stand on the precipice of new discoveries. The darkness that once hid 95% of the universe's content is slowly receding, giving way to insight. Bit by bit, the cosmos is yielding its secrets. The path ahead is still uncertain and filled with profound questions, but that is part of the allure. In probing the nature of dark matter and dark energy, we are, in a sense, probing the very soul of the universe, and in doing so, we learn more about our own place within it. The quest to understand this shadow universe is far from over. In fact, it may only be beginning. For nearly a century, scientists had been chasing the invisible gravitational glue of dark matter, slowly unraveling its cosmic role. But just as they began to piece together one mystery, another even stranger secret emerged. At the largest scales, the universe was behaving in a way no one expected. The cosmos, it seemed, was caught in a colossal tug-of-war between unseen forces. In the aftermath of the Big Bang, the universe expanded rapidly, carrying matter outward into the void. Over time, the pull of gravity, anchored by all that matter, both visible and dark, began to slow the expansion, much like a ball thrown upward that starts to lose speed. For billions of years, this cosmic breaking continued, gravity tugging against the initial explosive push. Galaxies drew together into clusters under gravity's sway. It was easy to imagine that given enough mass and time, the expansion might eventually halt, or even reverse into a grand collapse. Through much of the 20th century, astronomers debated the ultimate fate of the expanding universe. Did we live in a cosmos with enough matter to one day stop expansion in its tracks? Or would the universe expand forever, gradually coasting, but never quite stopping? The answer seemed to lie in measuring the universe's rate of slowdown, its deceleration under gravity. Observatories around the world set their sights on distant exploding stars, searching for clues in the flicker of ancient light. By the 1990s, teams of astronomers were meticulously charting these distant stellar explosions, supernovae, as cosmic mileposts. Each supernova flared with the brilliance of a billion suns, then faded away. Because their true brightness was known, these supernovae could serve as standard candles to gauge distances across the universe. Astronomers hoped that by using these cosmic yardsticks, they could measure how the expansion of the universe had changed over time. By comparing how bright they appeared to how bright they truly were, astronomers could determine how far away these stellar beacons lay, and how fast their host galaxies were receding from us. The expectation was simple. The farther back in time they looked, the more the universe's expansion should have been slowed by gravity. Distant supernovae should appear slightly brighter than expected, evidence that in earlier times, expansion was faster and had since been decelerating. For decades, this was the prevailing expectation among cosmologists. But when the data rolled in, it left scientists in disbelief. Those distant supernovae were not brighter than expected. They were dimmer. The supernova light had travelled a greater distance than anticipated, meaning the universe had expanded more since their light was emitted than anyone had predicted. Instead of slowing down, the expansion of the universe was speeding up. It was an astonishing revelation that defied all expectations. It was as if a hidden hand had pressed on the cosmic accelerator when no one was looking. At first, many scientists wondered if the result could be a mistake. The notion of an accelerating universe was so unexpected that alternative explanations were carefully considered. Perhaps, some suggested, there was hidden dust obscuring the distant supernovae, making them appear dimmer and thus falsely seem farther away. Others scrutinized the possibility of subtle biases in the data or unknown quirks of stellar explosions. But observation after observation upheld the baffling trend. Two independent teams, working on opposite sides of the globe, kept uncovering the same phenomenon. By the end of the 1990s, confidence grew that the acceleration was real. This extraordinary discovery was soon recognized as a landmark achievement, ultimately earning its discoverers the 2011 Nobel Prize in Physics, for it revealed a cosmos far stranger and more dynamic than previously imagined. In an instant, the narrative of a simple, gravity-ruled cosmos shattered. Gravity still pulled as always, but something else was pushing, gently, yet relentlessly. This push wasn't coming from any known source of energy or matter. It was diffuse, smooth, and imperceptible, except through its cosmic effects. Astronomers struggled for words. Some called it a dark force, or anti-gravity, but eventually one name took hold that hinted at its mysterious nature without pretending to understand it. Dark energy. Dark energy. The term itself reflected ignorance as much as insight. Dark because it was unseen and unknown. Energy because it seemed to behave like an inherent energy of space. driving expansion. Here was a new character in the cosmic story, one that had lurked undetected until the end of the 20th century. Its discovery didn't come from a particle caught in a detector, but from observing the universe on the grandest scales and noticing something fundamentally strange. This something acted like a subtle pressure, permeating the vacuum of space, pushing galaxies apart. It did not gather into clouds or clumps as matter does. Instead, it remained uniform, woven into the fabric of spacetime itself. The more space stretched, the more of this mysterious energy seemed to emerge, as if the very act of expansion conjured up more of the repulsive force. In effect, as the universe grew, dark energy's influence grew with it, eventually overtaking gravity's slowing pull. The cosmic tug-of-war between gravity and this new repulsive effect had taken an unexpected turn, one that would determine the future of everything. Scientists soon realized that this tug-of-war had been ongoing for eons. In the early universe, matter and the radiant energy of light was extremely dense, and gravity held the upper hand. Expansion was rapid after the Big Bang, but steadily slowing as gravity reined it in. If one could rewind time, galaxies in the past were rushing apart more quickly, then decelerating as the eons passed. At some critical moment, however, the balance shifted. Billions of years ago, when galaxies had grown distant and matter was more thinly spread, gravity's grip weakened just enough for dark energy to assert itself. The expansion, no longer sufficiently braked by the dwindling pull of matter, began to accelerate. The universe entered a new era, one dominated not by the gravity of matter, but by the repulsive push of dark energy. This transition was a cosmic tipping of the scales. Imagine a vast game of tug-of-war. On one side, invisible ropes of gravity woven by dark matter and galaxies, all pulling inward. On the other, a smooth but relentless pressure pushing outward on the fabric of space itself. For billions of years, the gravity side slowly gave ground. Around 5 to 6 billion years ago, roughly when our own sun and solar system were in their youth, the tug-of-war quietly turned in favor of dark energy. The expansion of space began to speed up. Galaxies that had been gently drifting apart were now picking up pace, moving faster as time went on. To observers within one of those galaxies, like us in the Milky Way, nothing seemed obviously different on a human timescale. The stars continued to shine, galaxies still wheeled in their orbits, and the night sky looked much as it had for millennia. Yet across the cosmos, the change was profound. With each passing million years, galaxies crept a little farther apart than they would have if only gravity were at work. Over billions of years, that difference became enormous. The universe was no longer coasting. It was sprinting ahead, propelled by an unseen agent of expansion. When the discovery of accelerating expansion was announced, the world of astronomy was stunned, but exhilarated. It's not every day that a whole new component of the universe is revealed. Dark energy, whatever it was, now had to be reckoned with in cosmic models. The realization sank in that we didn't inhabit a universe balanced on a knife edge between endless expansion and eventual collapse. Instead, a previously unimagined fate was in store, one where expansion wins out decisively over gravity's pull. As researchers absorbed this cosmic plot twist, they revisited Einstein's equations describing the universe's expansion. Decades earlier, Albert Einstein had included, almost reluctantly, a term in his equations, a cosmological constant, to allow for a static universe. At the time, without evidence of expansion, he imagined that gravity would make the universe collapse, so he introduced a repulsive term to counteract gravity and achieve a stable cosmos. Later, when Edwin Hubble discovered that the universe was expanding, Einstein reportedly scrapped that term, calling it his biggest blunder. The irony now was rich. Einstein's once abandoned cosmological constant suddenly seemed not only real, but essential, a possible representation of dark energy itself. The cosmological constant was a simple concept with uncanny implications. It suggested that empty space could possess its own energy, a persistent push that doesn't dilute as space expands. If dark energy was indeed this constant energy of the vacuum, it meant that as the universe grows, new space comes with new energy, fueling further expansion in a self-reinforcing cycle. On one hand, this neatly explained the data. A steady dark energy density would naturally lead to a slow acceleration that begins late and intensifies over time. On the other hand, it raised deep questions. Why would empty space have just this tiny amount of energy? And why had it become dominant at this particular epoch in cosmic history? With dark energy now in the picture, the inventory of the cosmos had to be rewritten. The vast majority of the universe's content was not in stars or gas, or even in dark matter's hidden mass, but in this new form of energy diffused through space. By the early 2000s, cosmologists refined their measurements and concluded that roughly 70% of the universe's total energy was dark energy, with about 25% in dark matter and a mere 5% in the ordinary matter that makes up stars, planets, and people. In other words, everything we experience directly, all the atoms of galaxies, gas, dust, planets, and our own bodies, amounts to only a tiny fraction of the cosmic pie. On the order of 95% of the cosmos is made of dark ingredients we do not yet understand, with dark energy being the lion's share. We truly live in a universe where truth is stranger than fiction. The invisible and unknown govern the visible and known. The tug of war continues even now, but the outcome seems clear. Dark energy is ascendant, and gravity's influence wanes as space expands further. Yet the exact nature of this dark energy remains elusive. The name gave it a label, but not an identity. In the unfolding cosmic story, dark energy quickly became the new protagonist, or perhaps antagonist, depending on one's perspective. It is the force that will determine the cosmic destiny, a shadowy presence pulling the strings of the universe's future. The stage was set for a new chapter of exploration. If dark matter was the invisible scaffolding holding the cosmos together, dark energy was the equally invisible gust of wind pushing the cosmos apart. Both were invisible. Both were essential. One pulled galaxies into clusters. The other drove clusters away from each other. One slowed cosmic expansion. The other sped it up. The delicate balance and struggle between these components would shape everything to come. Scientists around the world began to grapple with a flood of new questions. What exactly is this dark energy? How does it operate? Has it been constant throughout time, or could it evolve? Will it remain this way forever? The discovery of cosmic acceleration raised more questions than it answered. While dark matter was a riddle of unseen mass, dark energy was a riddle of unseen influence, an influence on the geometry and fate of the entire universe. In the afterglow of this revelation, one thing was clear. To understand the destiny of the cosmos, one would have to decipher the nature of dark energy. The cosmic tug-of-war, once assumed to be a battle solely between gravity and inertia, now had a new combatant. For the first time, the cosmic story had an unexpected player altering its course. It was no longer just gravity and motion. A new factor was rewriting cosmic destiny. and this shadowy contender was bending the course of cosmic history in ways scientists were only beginning to fathom. Dark energy had inserted itself as a central character in cosmology, demanding to be understood. With this profound shift in perspective, the journey turned toward unraveling the dark energy puzzle. An era of cosmology focusing on dark energy was now dawning. New questions emerged, and scientists prepared to grapple with them. They would soon find that investigating this dark force would challenge them as profoundly as the discovery itself. Dark energy was now an accepted part of the cosmic recipe, but knowing it existed was just the beginning. The mystery had only deepened. What exactly was this strange, all-pervading influence? Where did it come from, and why does it have the value it does? These questions hung in the air, puzzling scientists and inspiring new investigations. Unraveling the nature of dark energy became one of the foremost quests of modern cosmology. One of the simplest hypotheses was that dark energy might be the revival of an old idea, Einstein's cosmological constant. If so, it meant that empty space itself harbors a tiny, fixed amount of energy, a kind of built-in cosmological pressure. This concept was mathematically straightforward: a constant energy density filling space uniformly, exerting a negative pressure that drives expansion. It fit the supernova data well. As more evidence rolled in from other observations, the cosmological constant idea remained consistent. If dark energy is indeed a constant property of space, that implies it's the same today as it was billions of years ago and will be the same in the far future. Space, in this picture, is never truly empty. It always has this latent energy humming in the void. Yet calling it a constant didn't truly explain it. It just described how it behaves. Scientists were left asking, why does the vacuum have this energy at all? And why in this specific, incredibly small amount? Here was a deep puzzle. When physicists attempted to calculate the energy of empty space using quantum theory, the answers were absurdly large. Nothing like the gentle push we observe. In fact, theoretical predictions overshot the mark by an astonishing margin, by factors of trillions upon trillions. This error is so vast that it's often said to be the worst theoretical prediction in physics. Nature, it seems, found a way to almost nullify this vacuum energy, leaving just a tiny residue behind, just enough to influence cosmic expansion. The disparity between theory and observation was alarming, highlighting how poorly we understand the quantum vacuum and gravity when taken together. Solving this conundrum has become a central challenge, suggesting that something fundamental in our physics might be missing. Because of these puzzles, some researchers propose that dark energy might not be a true constant at all, but something dynamic and changing. They give it names like quintessence, reviving an ancient word for the fifth element beyond earth, air, fire, and water, a poetic nod to an ethereal substance filling the cosmos. In these models, dark energy could be a field permeating space, much like the electromagnetic field, but with very different properties. Perhaps it was weak in the past and will grow stronger in the future, or maybe it oscillates or decays over time. If quintessence or other exotic fields exist, they might cause subtle changes in the acceleration rate that careful measurements could detect. The idea that dark energy could evolve adds another layer of intrigue. It means the current balance of cosmic forces might not be permanent. The tug of war could slowly be changing its rules. The ultimate fate of the universe might differ from the simplest projection. This possibility keeps cosmologists searching for any hints that dark energy's strength or nature might change over time. Testing these ideas isn't easy. Dark energy doesn't emit light. We can't bottle it up in a lab or poke it directly. Its presence is inferred only through the behavior of the cosmos at large. So scientists have become clever, devising indirect methods to probe it. They look deeper into space and further back in time, observing how cosmic expansion has proceeded over eons. If dark energy has varied, the imprint of that variation should be written in the grand patterns of galaxies and in the faint light of distant epochs. Surveys of galaxies map how matter clumped together under gravity through time, offering clues to the push and pull that shaped that growth. The cosmic microwave background provides a precise snapshot of the universe when it was only 380,000 years old, long before dark energy took hold. And even that snapshot can serve as a baseline to gauge how much expansion has accelerated since. Additionally, special markers like baryon acoustic oscillations, subtle ripples in the distribution of galaxies, serve as a kind of cosmic yardstick. By measuring their size at different distances, scientists can tell how the expansion rate has changed. New telescopes and missions are being built with the express goal of deciphering dark energy's secrets. The Vera Rubin Observatory, perched high in the Chilean Andes, will survey the entire sky over and over, capturing billions of galaxies and supernovae, hoping to catch subtle shifts in cosmic expansion. The European Space Telescope Euclid is designed to peer deep into the distant universe with sharp clarity, mapping the distribution of galaxies and the bending of light by mass. NASA's Nancy Grace Roman Space Telescope will undertake similar studies, focusing on supernovae and large-scale structures to further illuminate dark energy's effects. These projects and others form a concerted, global effort. It is a kind of cosmic detective work. Instead of examining crime scenes, scientists examine ancient light from billions of years ago for clues to dark energy's behavior. The hope is to see whether the acceleration is changing over time or is truly constant, and thereby discern the nature of the force behind it. To many, this represents one of the grandest endeavours of modern astronomy. While observational astronomers chart the course of cosmic history, theoretical physicists attack the puzzle from another angle, in the realm of equations and fundamental laws. They ask how dark energy fits into the framework of physics that we know, or whether it demands something radically new. One possibility is that dark energy is connected to a concept in quantum physics known as zero-point energy, the idea that even a perfect vacuum seethes with temporary particles popping in and out of existence. If those microscopic fluctuations have an effect at large scales, they could manifest as a form of energy. But attempts to calculate this effect have failed to line up with the modest amount of dark energy observed. Another possibility is that our theory of gravity, Einstein's general relativity, might need modification on the largest scales. Perhaps gravity doesn't behave exactly as our equations predict when stretched across billions of light years. If that were true, what we call dark energy might actually be a sign of our theory's limitations, rather than a new energy field. There are speculative ideas of hidden dimensions, or multiverse scenarios, where what we perceive as dark energy is a kind of bleed over from other realms. But these remain highly theoretical and untested. Amidst all these hypotheses, the truth remains stubbornly elusive. Every time a new experiment or observation refines our measurements, dark energy continues to look uncannily like the simplest explanation. A tiny, constant energy woven into the fabric of space-time. Some scientists take comfort in that simplicity, while others are frustrated by the lack of clues to something deeper. The term dark in dark energy feels especially apt. This phenomenon is not just invisible to our eyes, it is dark to our understanding. It's as if the universe is whispering a secret, and we can catch only fragments of the words. The coincidence problem, as it's sometimes called, adds to the enigma. Why are we living in an era when dark energy is just starting to dominate? In the distant past, it was negligible compared to matter. In the far future, it will overwhelm everything. This may be pure chance, but it prompts contemplation. If dark energy had been significantly stronger early on, the universe might have expanded too fast for galaxies and stars to form. Conversely, if it had been much weaker, or negative, gravity might have won out early, leading to a recollapsing cosmos long before life had a chance to arise. We live in a universe where dark energy is present, but did not dominate until after galaxies formed, which has led some to muse about the anthropic principle. Perhaps only in such a finely balanced cosmos could observers like us have emerged to notice it. It's a philosophical notion as much as a scientific one, and it underscores the depth of the puzzle. The puzzle of dark energy cuts to the heart of fundamental physics and our place in the universe. We stand at a frontier. On one side is what we have learned and confirmed, a universe governed by known particles, forces, and a mysterious dark energy that acts like a cosmological constant. On the other side lies the unknown, a territory of theories waiting to be confirmed or discarded, of potentially new physics that could redefine how we see reality. It may be that answering the dark energy riddle will require a breakthrough as revolutionary as any in the history of science, just as quantum mechanics and general relativity once redefined our understanding of space, time, and matter. A new paradigm might be needed to reconcile dark energy with the rest of physics. Perhaps it will involve a bridge between the very large and the very small, uniting cosmology with quantum theory in an unexpected way. Or perhaps a fresh insight into gravity will emerge. Whatever the case, the pursuit of dark energy's identity promises to expand our knowledge in unforeseeable directions, challenging us to think beyond established paradigms. Through all of this, one thing remains clear. Dark energy is not an isolated curiosity. Fully understanding it is essential to a complete theory of the cosmos. Its existence appears to comprise about 70% of the universe and influences how galaxies and structures evolve over time. It must be accounted for in any theory that seeks to describe the universe from beginning to end. And that brings us back to the ultimate consequence of dark energy's dominion, the fate of the universe. While we toil to understand the essence of dark energy, we can at least explore its consequences. Dark energy will shape the cosmos's future, so exploring its effects is paramount. What does a universe dominated by this force look like as time marches on? The answers lie in the realm of cosmic destiny, and they paint scenarios both awe-inspiring and sobering. They range from a cosmos that slowly fades into darkness to one that ends in cataclysmic destruction. Each scenario offers a profound glimpse of how the cosmos may meet its end. Looking ahead, one comes face to face with the ultimate question. What is the fate of the universe, given the reign of dark energy? The most straightforward prediction, assuming dark energy remains a constant presence, is eternal expansion. In this scenario, the universe keeps growing forever, with galaxies accelerating away from each other. Over the next several billion years, the acceleration will become more and more apparent. Distant galaxies that are not bound to our local group will recede at increasing speeds. Eventually, their light will no longer reach us at all. They will slip beyond the horizon of our observable universe, like ships sailing over a distant ocean horizon, never to return. The night sky, which today is speckled with the faint glow of countless galaxies through our telescopes, will gradually lose those external lights. Future astronomers, living perhaps 100 billion years from now in a merged Milky Way Andromeda galaxy, might look out and find the universe strangely lonely. Beyond the stars of their own galaxy, they may see nothing but darkness, unaware that a vast cosmos once existed beyond, now invisible and unreachable. This outcome is often referred to as the Big Freeze, or heat death. It's a poetic term for a prosaic end. As expansion continues indefinitely, the energy of the universe becomes ever more dilute. Galaxies, or the remnants of merged galaxies, remain gravitationally bound in their own oases, but even within those islands of matter, change is inevitable. Star formation will slow and eventually cease. Stars are born from gas coalescing under gravity, but that supply is finite. In an accelerating universe, each galaxy or local group becomes an isolated star-making workshop that will eventually run out of raw material. Trillions of years from now, the last generation of stars will flicker to life. They may be dim red dwarfs, quietly burning their fuel over extraordinarily long lifespans. As these final stars exhaust their meager fuel, one by one they will wink out. In the darkness that follows, only stellar remnants will remain. Dense white dwarfs, slowly cooling like dying embers. Neutron stars and black holes standing as the ghosts of once brilliant suns. The cosmos will enter an era dominated not by shining stars, but by the faint afterglow of what once was. In those far future times, even these remnants undergo their own slow evolution. White dwarfs, over quadrillions of years, will radiate away their residual heat and fade into cold, black dwarfs, dark spheres of degenerate matter, essentially invisible. If protons, the building blocks of atoms, are unstable on immensely long timescales, then matter itself may gradually disintegrate into radiation and subatomic particles over eons unimaginable. Black holes, the last mighty bastions of mass, will not last forever either. Stephen Hawking theorized that black holes very slowly evaporate by emitting faint Hawking radiation. For a black hole as massive as our Sun, this process would take around 1067 years. For the supermassive black holes in galactic cores, the evaporation time is even more mind-boggling, on the order of 100 years or more. Yet, given enough time, even these giants should eventually dissolve, leaking away their mass in trickles of particles and photons into space. What remains after that final era? A thin haze of particles and energy, stretched across an ever-expanding emptiness. The universe would approach a state of maximum entropy, where no organized structures or useful energy gradients exist to power any process. It is a cosmos that has effectively gone to sleep, perhaps forever. Time would still continue, but with virtually nothing happening, the passage of eons would have no meaning. This quiet, cold, dilute expanse is the fate predicted if dark energy is an unchanging constant, pushing the universe onward. It is a somber vision, the death of the universe by gradual fading. But there are other possible endings to consider, especially if we entertain the idea that dark energy might not remain constant. If dark energy were to grow in strength over time, the future could be far more dramatic. Some speculative models of dark energy, often dubbed phantom energy, imagine an equation of state even more extreme than a cosmological constant. In such a scenario, dark energy's influence would increase without bound, and the acceleration of the universe would become runaway. Instead of merely pushing galaxies out of view, this phantom energy would eventually overcome all forces that bind structures together. This is the doomsday known as the Big Rip. In a Big Rip scenario, the expansion accelerates so fiercely that its effects reach down to smaller and smaller scales. Billions of years from now, in this hypothetical universe, galaxy clusters would be the first to feel the strain. Clusters of galaxies would be pulled apart as the space between them expands too fast for their gravity to hold together. Next, individual galaxies would disintegrate. Stars that were once bound in graceful spiral and elliptical orbits would drift away as their mutual gravitational bonds break. As time goes on, even solar systems could come unbound. Planets cast loose from their stars, no longer tethered to their suns. In the final moments before the Big Rip, perhaps mere minutes or seconds before the end, even atoms would not be spared. Space itself would be expanding so violently that it would rip apart the very bonds holding atoms together. Molecules, then atoms, and finally atomic nuclei would be rent asunder. The universe would meet a cataclysmic finale. Everything, down to the last particle, flying apart in a torrent of expansion. After that, what remains is hard to imagine. Perhaps just an ultra-fast dispersing mist of particles and radiation, a universe effectively torn to shreds. The Big Rip is a frightening prospect, but it's important to note that it's a highly speculative one. Current observations of dark energy do not indicate such extreme behavior. So far, dark energy behaves very much like a constant, not showing signs of growing explosively in strength. Even so, scientists remain watchful. If future measurements ever hinted at any such extreme trend, our expectations for the cosmic future would shift accordingly. For now, the Big Rip remains a dramatic thought experiment, illustrating just how strange dark energy could be if its properties were different from the simplest model. On the opposite end of possibilities, one might ask, could the universe ever stop expanding and recollapse, as was once considered before dark energy's discovery? This scenario is often called the Big Crunch, essentially a reversed Big Bang, where expansion halts and everything rushes back together in a fiery collapse. In a universe ruled only by matter and gravity, a Big Crunch is possible if there's enough matter to overcome the initial expansion momentum. For much of the 20th century, cosmologists wondered if our universe had enough matter for gravity to eventually win, or if it would expand forever. The discovery of dark energy altered that balance decisively. With dark energy in the mix, especially if it stays constant or grows, a Big Crunch becomes highly unlikely. The repulsive force doesn't weaken as space grows. In fact, its total influence grows as space expands, which makes a reversal seemingly impossible under our current understanding. However, for the sake of exploration, imagine dark energy were to somehow dissipate or even reverse in the far future. Say it's not truly constant, but something that might decay away or flip sign after unimaginable times. In that hypothetical case, the expansion could slow and eventually stop. Gravity, ever patient, would begin to pull everything back inward. Galaxies long separated by billions of light years might, over a stupendously long period, start drawing closer again. The darkness between galaxies would shrink as each galaxy's light becomes more visible to the others, now approaching rather than receding. Over an immense span of time, the entire universe would begin to contract. The cosmic microwave background, now a faint cold whisper, would heat up again as space compresses, eventually glowing brightly in the sky. Galaxies would collide and merge with increasing frequency. The night sky would no longer be dark. It would begin to blaze with the glow of infalling gas and the light of countless collisions. In the final phase of a Big Crunch, all space could collapse into a hot, dense state. Galaxies would be gone. Stars would smash into each other or be torn apart, and temperatures everywhere would soar to incandescence. The universe would become an ocean of fire, perhaps ending in an almost unimaginably dense point, a singularity, not unlike the state that started it all. Some theories have speculated that such a collapse could bounce into a new Big Bang, a cyclic universe scenario. But with what we observe now, this dramatic collapse seems to be off the table. It satisfies a certain poetic idea of a cosmos that regenerates. But given dark energy's presence, a big crunch appears nearly impossible unless dark energy itself somehow vanishes. Among these scenarios, the big freeze, the big rip, or a big crunch, the big freeze is most in line with current evidence. It is a vision of slow, quiet transformation rather than sudden destruction or rebirth. But all these fates share a reminder of the impermanence of cosmic structures and the vast, almost inconceivable timescales involved. For us, living in the flowering of the universe's history, the idea of all stars going dark or galaxies being flung beyond reach is deeply wistful. Yet, in a way, we are fortunate to exist at a time when the universe is vibrant and young, with galaxies clustering and stars lighting up the darkness. In the extremely distant future, the cosmos will not be so hospitable to complexity or life as we know it. The contemplation of the universe's fate can also highlight how special our present era is. Today, we can observe the cosmic microwave background, a baby picture of the universe, and see countless galaxies spread across the cosmos. We can measure the expansion and piece together the story of the universe from its fiery birth to now. But in an accelerating universe, far future observers might have none of these clues. The cosmic microwave background will, over trillions of years, redshift into obscurity, its faint glow stretched to undetectable wavelengths. Other galaxies, as noted, will have slipped away beyond the cosmic horizon. The evidence of the Big Bang and the broader universe will largely vanish from view. Intelligent beings in that far epoch might only see their own galaxy, or merged local cluster, and its stars. They might gaze into a black, starless expanse beyond, and wonder, without any way of knowing, what lies outside, never realizing that the universe was once full of galaxies, and that their own existence was made possible by a series of events, now hidden in darkness. In a sense, the universe in its old age will become more enigmatic to its inhabitants, hiding its past from them. This realization gives our current moment in cosmic time a poignant significance. We live in a brief window when the universe is old enough for intelligence to evolve, yet young enough that the sky still carries the signals of its origins and its vast expanse. It is as if we arrived at a grand theatre just in time to catch the full spectacle, from the opening act's afterglow to the dramatic formation of galaxies before the stage goes dark. Knowledge itself is a limited luxury of this era. The things we learn about the cosmos today might be impossible to learn in the far future, no matter how advanced a civilization becomes, because the clues will have disappeared. Of course, all these musings assume no new physics comes into play to drastically alter the narrative. There's always the possibility that our understanding of dark energy or other fundamentals could change. Perhaps dark energy itself is a temporary phase. Perhaps unknown phenomena might intervene over trillions of years that we currently can't foresee. Some have even speculated about exotic ideas, like vacuum decay. The notion that the very vacuum of space might someday transition to a lower energy state, essentially rewriting the laws of physics in an instant. That would be a cataclysm beyond comprehension, a true reset of the universe. It's a highly theoretical idea, with no evidence behind it. A faint reminder that even what we consider empty, stable space could hold surprises on unimaginable timescales. Yet, based on what is known and observed, the weight of evidence points to a universe that will simply continue to expand and cool. In that likely future, the drama is drawn out over trillions upon trillions of years, slowly trending towards stillness. It's a vision not of violence, but of gradual dimming. And while it may seem bleak from a human perspective, it is also serene in its way. A cosmos slowly settling into quietude after an age of brilliance and activity. Contemplating these futures can evoke a sense of cosmic solitude, but it also highlights how precious the present is. We are part of the universe at a time when it teems with galaxies, when stars burn bright and life can flourish, a time rich with light and possibility. In the timeline of the universe, these moments of starlight and life may be like a brief spark in a long night. And in that brevity lies meaning. It urges us to explore, to understand, to appreciate the cosmos we were born into. Our journey through the shadow universe of dark matter and dark energy has taken us from the smallest scales of particles to the grandest scales of cosmic destiny. These dark components, though invisible, shape everything we see and ultimately determine what will become of it all. There is a poetic symmetry in how dark matter and dark energy play opposite roles. One pulls structures together, the other pushes the expansion apart. Together, they governed the rise of cosmic structure and now the departure of those structures. Yet they remain mysteries at their core. We have mapped their influence, but not their essence. The pursuit of their true nature is ongoing, and each new discovery is like a piece of a puzzle that refines the story of the universe. As we stand now, at this midpoint in cosmic history, we have the unique opportunity to piece together the tale of our universe, from its fiery beginnings to the faint whispers of its far future. The work of scientists today, in observatories and laboratories around the globe, contributes to a narrative that future generations will continue. Bit by bit, the shadowy outlines of dark matter and dark energy are being filled in with understanding. We have come so far in illuminating the darkness, yet vast realms of the unknown still lie ahead. In the end, pondering the fate of the universe is a reminder of the enduring mystery and majesty of existence. It invites us to gaze upward and outward, to marvel at the cosmos, not just as a static picture, but as a dynamic story, a story in which we find ourselves deeply entangled. The shadow universe of dark matter and dark energy is, in many ways, the stage on which this cosmic drama unfolds. And though our journey through this chapter draws to a close, the quest to comprehend these mysteries and our own cosmic story continues ever onward, guiding us into the next chapter of discovery. We gaze out at the glittering tapestry of the night sky and see the brilliance of stars and galaxies scattered across the darkness. Yet this familiar cosmic panorama is misleading, because most of what exists in the universe remains invisible to our eyes. The darkness between those stars is vast, and within it lie secrets we are only beginning to suspect. The gentle glow of nebulae and the shining arcs of the Milky Way are merely surface features on a vast ocean of unseen substance. It is as if we have been admiring the bright foam atop a deep wave without realizing the depths of the ocean below. Beyond the reach of our telescope's light lies an elusive domain, a shadowy presence that neither emits nor reflects the light by which we navigate. and yet profoundly influences the cosmos we know. In the stillness of space, an unseen universe surrounds us, silent and mysterious, waiting for us to recognize its existence. The cosmos we celebrate in photographs and through our telescopes is in fact only a thin veneer over a much larger reality. For every glowing star or swirling galaxy we can observe, there is vastly more mass lurking in the dark, unseen. Astronomers have come to realize that the familiar matter we perceive, all the planets, stars, gas, and dust, makes up only about 5% of the universe's content. The rest is composed of two mysterious ingredients, one that holds galaxies together in its gravitational embrace, and another that drives the expansion of the universe ever faster. These are known simply as dark matter and dark energy. Dark, not because they are sinister, but because they lie hidden from direct view, detectable only through their profound effects on the cosmos. Decades ago, the first clues to this hidden mass emerged quietly in the observations of distant galaxies. Astronomers measuring the motions of galaxies within clusters found that those galaxies were moving far too swiftly to be held together by the gravity of the visible matter alone. Something invisible seemed to be adding extra gravity, preventing the clusters from flying apart into the void. Astronomer Fritz Zwicky, who first calculated this missing mass in a distant galaxy cluster in the 1930s, famously dubbed it dark matter, matter that revealed itself only by its gravity and not by any light. Years later, in the spiral arms of individual galaxies, another surprise was uncovered. Stars, orbiting in the far outskirts, were whipping around faster than they should, as if pulled by an unseen gravitational force. The luminous mass of those galaxies, the shining stars and glowing clouds of gas, wasn't nearly enough to explain such rapid rotation. Nature, it seemed, had hidden a vast amount of matter in the dark, revealing its presence only through the subtle yet relentless tug of gravity. In the 1970s, astronomer Vera Rubin spent countless nights observing the speeds of stars in galaxies like our neighbouring Andromeda. What she found defied expectations. Stars far from a galaxy's centre were moving just as fast as those nearer in, instead of slowing down. This flat rotation curve was a clear sign that a huge amount of unseen mass surrounds each galaxy. Rubin's meticulous work provided some of the most convincing evidence yet that dark matter was real, not just lurking in distant clusters, but wrapped around every galaxy, including our own. Her discovery marked a turning point, the moment when the invisible component of the cosmos could no longer be ignored, forcing scientists to accept that we live in a universe largely made of something we cannot see. Another line of evidence for this hidden mass came from the way its gravity bends light, a phenomenon known as gravitational lensing. Distant galaxies sometimes appear distorted or smeared into arcs and rings in the sky, their light curving on its journey to us. Often, the culprit is a massive concentration of matter in the foreground. Yet when astronomers tally up all the visible material at that spot, it falls short. The light is being bent far more than the observed stars and gas could manage alone, implying a heavy invisible presence adding to the gravitational lens. This ghostly mass, although unseen, announces itself by the way it warps the fabric of space and redirects light. Sometimes these distortions coalesce into elegant shapes, such as elongated arcs, or even almost complete rings of light, known as Einstein rings, encircling a mass that itself remains invisible. These ethereal patterns in the sky are direct visual clues to the hidden gravitational landscape sculpted by dark matter. By analysing them, astronomers can map the distribution of the unseen mass, effectively making the invisible visible through its effects. Perhaps the most dramatic illustration of dark matter's reality occurred when scientists observed a pair of galaxy clusters that had collided in a cosmic accident. As these two enormous groups of galaxies passed through each other, the clouds of hot gas within them, which glow in X-rays and are made of ordinary matter, crashed and slowed down. The gas from both clusters piled up and heated in the middle, like cars crumpling together in a cosmic traffic jam after a collision. However, the majority of the cluster's mass did something unexpected. It simply kept going, passing straight through the smash-up with hardly any resistance. Astronomers mapped where the mass ended up by observing how it bent background light, and discovered that the bulk of the mass had moved ahead of the luminous wreckage of gas. In other words, the invisible matter had effectively slipped through the scene unimpeded, leaving the ordinary matter behind. This stark separation provided a powerful confirmation that dark matter is a distinct entity in the cosmic drama, an unseen component wielding enormous influence. Unlike the everyday matter that makes up planets and people, this dark matter does not emit or absorb light at all, which is why it remained hidden for so long. It neither shines nor blocks light. It is transparent and ghostly, interacting through gravity, but little else. Whatever dark matter is made of, it must be fundamentally different from the protons, neutrons, and electrons that build the atoms around us. If it were composed of familiar particles, we would see its effects in laboratory experiments or detect the light it gives off in space. Instead, it behaves as if it were a new kind of matter entirely, one that drifts through the cosmos largely unseen, only revealing itself indirectly by sculpting the orbits of stars and bending the path of light. What could this dark matter actually be? Over the years, scientists have speculated on various possibilities. Early on, some wondered if the missing mass might simply be made of ordinary but faint objects, perhaps swarms of dim stars, burnt-out stellar remnants, or even undiscovered black holes hiding in the darkness. However, careful searches and calculations showed that such ordinary objects cannot account for the vast amount of unseen mass permeating the universe. The consensus has shifted toward the idea that dark matter consists of something more exotic, likely new kinds of subatomic particles that have so far escaped detection. Perhaps they are heavy, slow-moving particles that seldom interact with normal atoms, whimsically nicknamed WIMPs, meaning weakly interacting massive particles. Or they could be incredibly light and plentiful particles known as axions, forming a gentle, pervasive background field across space. These and other hypotheses paint a range of possibilities, but so far, no definitive clue has emerged. The true identity of dark matter remains elusive, a riddle that nature has yet to answer. For a time, some researchers wondered if dark matter might actually be ordinary matter hiding in unusual places. They imagined swarms of dim, compact objects in the halos of galaxies, things like burnt-out stars, brown dwarfs, failed stars that never ignited, rogue planets, or even ancient small black holes. In astrophysical slang, these hidden heavy objects were dubbed machos, short for massive astrophysical compact halo objects. If enough of them existed, their combined gravity could potentially account for the missing mass. Astronomers devised surveys to search for machos, often using the tool of gravitational lensing. They monitored millions of background stars, watching for telltale flickers of light. If a massive compact object drifted in front of a distant star, its gravity would act as a lens, briefly magnifying the star's light. Such microlensing events were observed, implying there are indeed some dark objects wandering the galactic outskirts. However, the number of events was far too small to explain the enormous quantity of dark matter. Ordinary hidden objects, faint stars, drifting planets, or primordial black holes could contribute only a small fraction of the invisible mass. The rest, by elimination, had to be something truly new, not made of the protons and neutrons of everyday matter. On galactic scales, we now believe that every galaxy, including our own Milky Way, is embedded in a vast halo of dark matter. This halo envelops the galaxy like an invisible cocoon, extending far beyond the furthest visible star at the galaxy's edge. If our eyes could somehow see this dark matter directly, we would behold each galaxy surrounded by a gargantuan dim aura, a globe of gravity that outweighs all the stars within it. This invisible halo acts as cosmic glue, its gravitational grip keeping the galaxy intact and the stars bound in their orbits, preventing them from drifting off into space. From an impossibly distant vantage point, one could see that galaxies are not scattered randomly through space. They trace an intricate pattern, a vast cosmic spiderweb woven of matter. Great filaments stretch for hundreds of millions of light years, connecting clusters of galaxies at their intersections. Immense voids lie in between like dark, empty bays between strands of the web. This grand design, often called the cosmic web, is largely the handiwork of dark matter. The galaxies we see are like beads of dew caught on an invisible web. They shine brightly at the nodes and along the threads, but the web itself is dark. Dark matter's gravity provides the scaffolding for this structure, drawing ordinary matter into the dense knots and filaments where galaxies ignite and grow. Without the guiding pull of this shadow framework, the universe would likely have lacked much of the rich clustering of galaxies that we observe. The cosmic web as we know it owes its form to the unseen mass holding it all together. Interestingly, evidence for dark matter is also written across the oldest light in the universe, the cosmic microwave background. This faint afterglow of the Big Bang carries subtle ripples, slight differences in temperature that reflect sound waves in the primordial plasma. The pattern of those ripples lines up perfectly with a universe filled with dark matter. If there were only normal matter, the cosmic afterglow would look different than what we observe. The fact that our measurements of this ancient light fit the dark matter model is yet another affirmation that, even in the universe's infancy, the invisible mass was already at work, gently steering the formation of structures that would later grow into galaxies and clusters. The surprises of the unseen universe did not end with dark matter. In 1998, astronomers probing the expansion of the cosmos uncovered an even stranger phenomenon lurking in the void. By observing distant exploding stars, delicate beacons known as supernovae, they attempted to measure how the universe's expansion rate had changed over time. The expectation was that the expansion should be slowing down, ever so gradually, pulled back by the gravity of all the matter in the universe. Instead, these distant supernovae appeared dimmer and farther away than anticipated, a cosmic clue that sent a shiver of astonishment through the scientific community. It was as if the universe had somehow hit the gas pedal. The expansion of space was not slowing, but accelerating. The discovery of the accelerating universe was met with astonishment, even a bit of healthy skepticism at first. But in the years that followed, multiple independent lines of evidence began to converge on the same reality. Detailed surveys mapped how galaxies are distributed in space and how the universe's large-scale structure grew over time. Those observations, along with precise measurements of the cosmic microwave background's subtle patterns, all pointed to one conclusion. Some form of unseen energy must be permeating space. One by one, alternative explanations fell short, and the concept of dark energy gained traction as a central component of our cosmological model. In 2011, the leaders of the teams that discovered cosmic acceleration received the Nobel Prize in Physics, a testament to how profoundly this finding reshaped our understanding of the universe. What began as a shocking revelation is now an integral part of the cosmic story, even if it raises as many questions as it answers. Scientists came to accept that our universe is dominated by this mysterious dark energy, and the task at hand shifted to understanding its nature. To explain the bewildering discovery that the cosmos is speeding up, scientists introduced the idea of an unseen energy inherent to space itself. They named it dark energy. Dark because its nature is unknown and it cannot be seen, and energy because it behaves as a form of energy spread throughout the vacuum of space. In essence, even the emptiest void isn't truly empty. It carries a subtle pressure, a built-in tendency for space to push outward. This dark energy imbues every region of space with a faint repulsive effect, counteracting gravity on the largest scales and driving the expansion of the universe to accelerate. The amount of energy involved is incredibly small in density. By some estimates, each cubic meter of vacuum contains only enough energy to light a single bulb for an infinitesimal fraction of a second. Yet because space itself is so vast, even this whisper of energy pervading every nook of the cosmos adds up to an immense influence. In a twist of fate, this concept had been hinted at long before. Albert Einstein, when formulating his theory of general relativity, once added a term to his equations, the cosmological constant, to balance the universe against collapse or expansion. He later discarded it, calling it his biggest blunder when it seemed unnecessary. But decades later, the notion of a cosmic repulsive force resurfaced with dark energy. What Einstein had treated as a mathematical fix turned out to correspond to something real, an intrinsic energy of space that pushes the cosmos outward. Dark energy, in effect, appears to be a manifestation of that long-ago cosmological constant, a quiet, pervasive force woven into the fabric of space-time, gently but relentlessly urging space to expand faster and faster. Today, dark energy is considered the single largest ingredient of the cosmos. By the best estimates, nearly 70% of the total energy in the universe is tied up in this mysterious form. Dark matter constitutes roughly another 25%, and the ordinary matter we are familiar with amounts to less than 5%. In other words, the stuff we can actually see is only a tiny sliver of existence. The vast majority is dark and unexplained. Dark energy behaves very differently from dark matter. While dark matter gravitates and clumps together around galaxies and clusters, dark energy does not clump at all. It appears to be spread evenly throughout space, like a smooth background presence. You cannot point a telescope to see a specific blob of dark energy. It seems to reside uniformly in every corner of the universe, even in the enormous voids between galaxies. Its effect is imperceptible on small scales, but over the immense distances between galaxy clusters, this subtle pressure adds up. As space expands, dark energy's influence grows with it, providing a kind of ever-present push that becomes more dominant as the universe becomes larger and more empty. If dark energy remains constant and continues to dominate, it will dictate the ultimate fate of the universe. As time marches on, the repulsive push of dark energy grows ever more significant relative to gravity. Distant galaxies that are not bound to our own will recede faster and faster, eventually slipping beyond the horizon of what we can observe. Far in the future, on the scale of trillions of years, an observer in our Milky Way might gaze outward and find nothing but darkness beyond the nearby galaxies. All other galaxies would have been driven forever out of sight by the relentless expansion. The cosmos would become a much lonelier place, with each surviving island of matter isolated amid a vast, ever-growing sea of emptiness. This far future vision is sometimes called the Big Freeze, a final state in which the universe expands so much that galaxies use up their fuel and new stars no longer form. With each passing eon, existing stars will die out and no new lights will replace them. The result would be an extremely cold and quiet cosmos. The faint glow of the last red stars would eventually flicker and fade to black, leaving a universe that is dark and nearly empty. It is a somber outcome to contemplate, but it lies in an almost inconceivably distant future. For billions upon billions of years to come, stars will continue to be born and shine. Galaxies will collide and merge, and perhaps life will endure to marvel at the cosmos. All the while, dark energy will be working ever so gradually in the background, gently steering the universe toward that far-off horizon of emptiness. The revelations of dark matter and dark energy have fundamentally reshaped our picture of the cosmos. Where once humanity believed that the glittering galaxies and shining stars were all that existed, we now understand that we are awash in a sea of unseen influences. The universe, it turns out, is dominated by the invisible, a kind of shadow realm of matter and energy that we can only sense through subtle clues. These discoveries are both humbling and inspiring, reminding us that reality holds far more than meets the eye. Scientists around the world have taken up the challenge of illuminating this darkness, determined to learn what these mysterious ingredients are. But how do you detect what cannot be seen? How do you study forces that evade all direct measurement? With ingenuity and persistence, researchers have devised clever experiments and observations to chase these shadows. The quest to understand the dark universe is well underway, and each new finding brings us a step closer to unveiling the secrets of dark matter and dark energy. It is a journey filled with challenges and wonder, and it has only just begun. All around the world, scientists have responded to the challenge of the dark universe with determination and creativity. The quest to understand dark matter and dark energy is underway in many forms, unfolding in high mountain observatories, deep underground laboratories, and even far above Earth in space. In one sense, the whole planet has become an extended sensor for these cosmic mysteries, with different teams tackling the problem from every conceivable angle. Even as we speak, in a quiet vault a mile beneath the ground, a detector sits in darkness, listening for the faint knock of a dark matter particle. On a mountaintop, under a clear night sky, telescopes capture the light of distant supernovae and galaxies, searching for subtle clues of dark energy's influence. In an accelerator facility, protons are being hurled against each other at near light speed, their collisions watched for traces of new particles. This global, multi-pronged effort represents humanity's collective attempt to illuminate the unknown. Each approach is like a different sense organ, feeling out a part of the dark puzzle, and together they bring us closer to insight. Deep beneath the Earth's surface, far below the reach of most cosmic rays, lies a cavernous laboratory filled with strange and silent apparatus. In one such subterranean chamber, a great tank of liquid xenon stands at the ready, surrounded by rings of ultra-sensitive sensors. Scientists built this instrument to listen for an exceedingly rare whisper in the dark, the faint signal of a dark matter particle colliding with an atom within the liquid. Thick shields of rock and metal block out the natural radiation of the world above, and an array of photomultiplier tubes gazes intently into the transparent liquid, waiting for a tiny flash of light or a subtle electric pulse that would betray the long-awaited encounter. Time passes quietly in these underground halls. Days and nights lose their meaning deep in the mine. Months and years of data collection roll by with no fanfare. Most of the time, nothing at all is seen aside from the dull glow of occasional background interactions. Yet the scientists remain patient and hopeful. They know that if even one dark matter particle were to strike an atomic nucleus in their detector, it would produce a fleeting signal, a definitive wink from the cosmos, that could confirm the particle nature of dark matter. That single event, if it comes, would illuminate a piece of the shadow universe, turning a decades-old hypothesis into a tangible discovery. To even have a chance of catching such a rare event, scientists go to extreme lengths to eliminate every possible false signal. The detectors are cocooned in multiple layers of shielding. Often, an outer tank of ultra-pure water or scintillating liquid surrounds the experiment to catch and veto charged particles coming from space. Closer in, layers of lead, polyethylene, or other materials block neutrons and gamma rays that could emanate from the cavern walls. Every construction material is carefully selected for its radio purity. The metal components, the crystals or liquids inside the detector, even the air in the chamber, are all scrutinized so that nothing gives off unwanted radiation. Some experiments operate at cryogenic temperatures, chilling their sensors to near absolute zero to reduce thermal noise and random vibrations. The effect is to create an oasis of almost unnatural quiet around the detector, a stillness in which a whisper of dark matter might be detected. Through these Herculean efforts at background reduction, scientists do everything humanly possible to give their experiment a clear listening space. Now, all that is left is to wait and listen with patience. Around the globe, multiple experiments are engaged in this grand hide-and-seek with dark matter. In laboratories beneath Italian mountains, in former gold mines in the United States, and in deep shafts in Asia, different detectors sit in vigil. Some are vats of noble liquids, like xenon or argon, designed to scintillate with a flash of light if a dark particle strikes. Others use solid crystals, cooled to near absolute zero, so that even the smallest deposit of energy from an interaction produces a measurable vibration. Each approach is different, but all share one goal: to catch a trace of the elusive dark matter particle at last. With each passing year, these experiments have become more sensitive and ambitious. Early dark matter detectors were small and could have missed all but the most strongly interacting particles. Today's detectors are feats of engineering on a grand scale, multi-ton chambers of ultra-pure liquid, or arrays of crystal sensors tuned to atomic delicacy. Scientists have learned to shield them better from stray radiation by going deeper underground and using cleaner materials than ever before. Every component is carefully chosen to be low in radioactivity, every fluctuation meticulously accounted for. The result is that the newest generation of experiments can detect signals far fainter than what was possible just a decade ago, opening new frontiers in the search. There have even been moments of excitement when a detector hinted at something unusual. For instance, One long-running experiment, deep under a mountain in Italy, has observed a subtle annual fluctuation in its data, a periodic signal that rises and falls with the seasons. Some scientists speculated that this could be the Earth's motion through the galaxy's dark matter halo, causing the detector to encounter slightly more dark matter particles at one time of year and fewer at another. It was exactly the kind of patterned signal one might hope for as evidence. However, other experiments with similar setups did not detect the same effect. Was it truly a dark matter signature? Or could it be explained by ordinary seasonal changes in the environment, like tiny variations in detector conditions or background radiation? To this day, the Italian finding remains an intriguing puzzle, but not a confirmed discovery. It serves as a vivid example of how the dark matter hunt is filled with tantalizing hints that demand careful scrutiny. Researchers stay both hopeful and cautious, excited by potential signals, yet determined to verify every clue from multiple angles before declaring a discovery. What if these detectors see nothing? So far, that has been the case. No confirmed dark matter signal has appeared. Yet in science, even an absence of evidence can guide the way forward. Each time an experiment finds no hint of dark matter, it further constrains what dark matter could be, tightening the bounds on its possible properties. It is like mapping an unknown land by ruling out where something is not, gradually closing in on where it must be. Rather than discouraging the community, these results have sparked new ideas and greater determination. The pursuit continues with patience and optimism, driven by the knowledge that a discovery might come with the next leap in sensitivity, or perhaps through a completely new approach that has yet to be imagined. Not all dark matter searches focus on heavy, rare collisions. Some scientists are pursuing a very different clue: the possible existence of an ultralight particle known as the axion. If axions exist, they would be almost ghost-like, but under the right conditions, they might subtly convert into light. In specialized laboratories, researchers set up powerful magnetic fields and sensitive radio antennas, hoping to catch an axion transforming into a faint electromagnetic tone. Essentially, they are listening for a quiet radio hum that an axion would produce, like trying to hear a single specific note in a sea of static. This approach is quite unlike the giant underground detectors or the high-energy atom smashers. It's more of a delicate eavesdropping on the whisper of the cosmos. Yet it represents another important front in the dark matter hunt. The diversity of methods, from massive liquid xenon tanks and supercooled crystals to whispering microwave cavities, shows how scientists are leaving no stone unturned. With creativity and persistence, they are probing every conceivable way dark matter might reveal itself, determined to catch its signal by any means possible. Laboratory experiments aren't the only way to hunt for dark matter. Some scientists turn their sights to the cosmos itself, looking for indirect traces of dark matter's handiwork. If dark matter particles can annihilate each other or decay, they might produce a faint glow of ordinary particles and radiation. By examining the sky with sensitive telescopes, researchers search for any unusual excess of high-energy light, gamma rays or X-rays, or an unexpected abundance of cosmic rays that could be the fingerprints of dark matter interactions far out in space. There have indeed been tantalizing hints. A space-based experiment, for example, has observed more high-energy positrons, the antimatter equivalents of electrons, than expected. One possible interpretation of this surplus is that dark matter particles out in space might occasionally collide and annihilate each other, producing positrons as byproducts. And near the center of our Milky Way, telescopes have found a subtle glow of extra gamma rays that doesn't neatly fit known sources. Another possible hint of dark matter gathered in our galaxy's core. However, None of these signals are a smoking gun. Each anomaly, whether the positron surplus or the extra gamma rays, might yet be explained by ordinary astrophysical phenomena, perhaps undiscovered pulsars or some other high-energy process. The jury remains out, but these hints remind us that dark matter could reveal itself in indirect ways. They spur scientists to keep watching the cosmos for subtle signs. The hunt for dark matter is not confined to underground labs. It also extends to the skies. Someday, we might catch dark matter, leaving its mark in the patterns of cosmic particles and light. In the realm of high-energy physics, another tactic is to try to create dark matter in the laboratory. The Large Hadron Collider, a 27-kilometer ring deep underground on the French-Swiss border, accelerates protons to nearly the speed of light and crashes them together by the billions. These collisions recreate tiny fireballs similar to the conditions just after the Big Bang, with the possibility of birthing exotic particles. Scientists hope that among those newborn particles could be dark matter, showing up transiently in the debris of a proton smash. Dark matter itself would glide through the collider's detectors without leaving a direct mark. But physicists have clever ways to infer its production. They look for collisions where energy and momentum appear to vanish, as if something invisible carried away a chunk of the energy. Such missing energy events are like footprints left by a ghostly particle escaping the detector. If a significant number of these events were observed with the right characteristics, it would strongly suggest that dark matter particles had been created in those high-energy collisions. So far, however, the LHC's searches have not yielded any clear evidence of dark matter or other new particles. This was a bit of a surprise. Many theories had predicted that something unexpected might show up at the energies the LHC can reach. The continued absence of new particle signals has prompted physicists to refine their ideas and consider that dark matter could lie just beyond our current experimental grasp. Many scientists had pinned hopes on a theoretical idea called supersymmetry, which predicted a host of new particles, one of which could have been a perfect dark matter candidate, appearing at high energies. But as the LHC ran through its first decade, no such particles materialized. Undeterred, the scientific community is already planning even mightier accelerators for the future. By reaching higher collision energies and probing with greater precision, they aim to extend our reach into the unknown. Perhaps with the next generation of colliders, the subtle fingerprints of dark matter will finally emerge from the subatomic smash-ups. It is another example of how every avenue is being explored. From deep underground detectors to space telescopes to colossal particle colliders, no stone is left unturned in the quest to bring the shadowy particles of dark matter to light. In the course of the dark matter quest, some researchers have explored more radical possibilities. One idea suggests there might be no dark matter particle at all. Perhaps the laws of gravity themselves need modification. If gravity behaved slightly differently on the scale of galaxies, it could potentially explain why stars orbit faster in galactic outskirts without invoking unseen mass. Such modified gravity theories can be tuned to match galaxy rotation curves by effectively making gravity a bit stronger or fall off more slowly at low accelerations. For a time, this concept offered a tempting alternative to the dark matter hypothesis. However, it has proved difficult for any tweak to gravity to account for all the evidence. Observations like the bullet cluster, where mass appears separated from normal matter, are hard to explain without invoking some invisible mass. Moreover, the subtle ripples in the cosmic microwave background align neatly with models that include dark matter, but would be hard to reproduce with modified gravity alone. Due to these challenges, most scientists are convinced that dark matter is real and made of something new. Still, exploring such alternatives has value. It keeps minds open. The universe has a way of surprising us, and even unconventional ideas are worth exploring on the path to understanding this mystery. Dark energy, too, has prompted a range of creative ideas. Perhaps this mysterious force is not a constant, but something dynamic, a field that slowly changes over cosmic time. In this scenario, often called quintessence, the strength of dark energy might increase or decrease over time, potentially altering the universe's fate. Scientists are searching for any sign that dark energy's influence has shifted over billions of years by examining the history of cosmic expansion. So far, observations suggest that dark energy behaves like a constant push within the limits of current measurements. But it's still possible that subtle evolution is hiding. New missions and surveys, such as the European Space Telescope Euclid, will further test whether dark energy is indeed unchanging or if it conceals any time-varying secrets. Another perplexing question is why dark energy is so extremely small in magnitude. If it truly represents energy inherent in empty space, Einstein's cosmological constant, our theories of quantum physics struggle to explain how it can be so feeble. In fact, simple calculations suggest vacuum energy should be vastly larger, enough to rip the universe apart before galaxies ever formed. To bridge this gap, some physicists have floated bold ideas. One proposal is that our universe might be just one of an enormous number of universes, each with different properties. In such a multiverse scenario, dark energy could vary from universe to universe. We would naturally find ourselves in one of the rare universes where dark energy is extraordinarily small, because only in those universes would structures like galaxies, stars, and living beings have the time to come into existence. This line of reasoning, using what's called the anthropic principle, is controversial and currently impossible to test. Still, it highlights the lengths to which scientists will go in contemplating solutions to the dark energy problem. Another line of inquiry asks whether dark energy might not be a substance at all, but rather a sign that our understanding of gravity could be incomplete on cosmic scales. Could it be that Einstein's general relativity needs a subtle modification when it comes to extremely large distances or low-density environments? If gravity were altered just enough, it might naturally lead to an accelerating expansion without invoking any mysterious energy field. Scientists have devised various modified gravity models to see if they can replicate the observed acceleration. These theories adjust the equations of gravity in different ways, aiming to eliminate the need for dark energy by making the expansion speed up on its own. So far, however, none of these alternative gravity ideas has matched the precise observations of our universe, as well as the simpler explanation involving dark energy. The way galaxies cluster together, the subtle patterns in the cosmic microwave background, and the historical record of expansion traced by distant supernovae all align comfortably with Einstein's gravity plus a cosmological constant. Modified gravity models have yet to provide an equally tidy fit to all these pieces of evidence. In other words, as strange as dark energy is, it still best accounts for what we see. Thus, dark energy endures as the leading explanation for the accelerating cosmos, a perplexing ingredient at the heart of modern cosmology. It remains a profound mystery, perhaps a clue that will one day lead to new physics beyond our current theories. For now, scientists forge ahead, scrutinizing each new batch of astronomical data for hints and refining their models of the universe. With every new survey of galaxies, for instance, Upcoming observatories like the Rubin Observatory on Earth or the Euclid and Roman space telescopes, every map of cosmic microwave background fluctuations, and every improved measurement of the expansion rate, they hope to inch closer to the truth. Hidden in those troves of data, or in the equations yet to be written, could be the key that finally unlocks the secret of this shadowy energy dominating our universe. Despite all these efforts, dark matter and dark energy remain unsolved mysteries. We have narrowed the possibilities and learned much about what they do, yet their true nature still eludes our grasp. This state of not knowing is not a failure. It is the very essence of science, the edge of the map where knowledge meets mystery. It is here, on this frontier, that the next great discoveries await. Rather than be discouraged by the darkness, scientists find themselves inspired by it. They embrace the unknown, recognizing it as the frontier that drives their journey forward. In facing these cosmic mysteries, we are reminded of the spirit of discovery itself, the willingness to venture into darkness, guided by curiosity and wonder, until one day it becomes light. Throughout history, confronting the unknown has often led to humanity's greatest insights. There was a time when many forces and phenomena, electricity, magnetism, X-rays, were invisible mysteries, until curiosity brought them to light. In the 19th century, a strange wobble in the orbit of Uranus hinted at an unseen presence. By embracing that celestial anomaly, astronomers calculated and discovered Neptune, a new planet hidden in the dark. Early in the 20th century, physicists noticed energy seemingly disappearing in certain radioactive decays. Instead of dismissing the discrepancy, they boldly proposed a new particle, the neutrino, a ghost of matter so elusive it took decades to detect. Eventually, neutrinos were found, confirming that what was once an unseen conjecture was a real part of nature. These examples remind us that mysteries are not roadblocks, but signposts pointing toward deeper truths. Every time we acknowledge our ignorance and press forward, the boundaries of knowledge expand. The dark matter and dark energy of today are heirs to those past enigmas, puzzles that challenge us to sharpen our tools and widen our perspective. By grappling with them, we stand to unlock profound new understandings of the universe. In confronting the invisible, we are following a long tradition of discovery, one that has always rewarded patience and imagination with a richer view of reality. It is profoundly humbling to realize that everything we have ever seen, all the galaxies, stars, planets, and even the atoms in our bodies, comprises only a tiny fraction of what exists. The bulk of the universe lies in forms we cannot yet directly perceive. But rather than diminishing us, this revelation is inspiring. It means there is far more to learn, and that our cosmic journey is far from over. In rising to meet this challenge, humanity finds a rare unity of purpose. The quest to understand dark matter and dark energy is a truly global enterprise. Scientists from all over the world share data, ideas, and insights, collaborating across cultures and borders to solve these cosmic riddles. In the face of the unknown, we are all simply seekers of knowledge, collective explorers pushing into the cosmic dark, hand in hand. This shared pursuit reminds us that the mysteries of the universe belong to everyone, and the answers, when they come, will be a triumph of the human spirit as a whole. Acknowledging our ignorance is not only humbling, it is also the first step toward profound discovery. Grappling with dark matter and dark energy could spark a revolution in science. If we identify what dark matter is, we might find it's not an isolated phenomenon at all, but a gateway to a whole hidden side of nature, perhaps an entire family of particles, or even new forces that have been around us unseen since the dawn of time. Such a discovery would extend the known inventory of the universe and deepen our understanding of how matter and forces work. Cracking the enigma of dark energy could likewise revolutionize our understanding of fundamental physics. This mystery touches the very fabric of space and time, hinting at a connection between gravity and quantum physics that we have yet to fully grasp. Solving why the cosmos is accelerating might demand entirely new principles, perhaps a bridge between the physics of the very large and the physics of the very small. It challenges us to extend or rethink Einstein's legacy, and it might ultimately guide us toward a deeper unity of nature's laws. These grand mysteries compel us to think big and question deeply. In the attempt to illuminate the darkness, we find ourselves pushing the limits of technology and creativity, building ultra-sensitive instruments, devising novel experiments, and harnessing global computing power. The quest for answers drives innovation that can ripple out into other fields and everyday life. And beyond practical benefits, there is an intellectual and spiritual enrichment in the pursuit itself. By striving to understand the dark universe, we may end up not only solving specific puzzles, but also revealing new layers of reality that we never suspected. The payoff could be a radical transformation of how we see the world, a shift as profound as any that science has achieved before. There is a peculiar beauty in the unknown. Mystery inspires wonder, and wonder is what drives us to seek understanding. If everything in the cosmos were already neatly explained, would the night sky stir our souls as deeply? The very fact that so much remains unexplained means the universe still has its secrets, retaining an endless capacity to surprise and astonish us. When we gaze up at the stars, knowing that invisible matter guides their motions, and some inscrutable energy quickens the expansion of space, we cannot help but feel a profound awe. We are confronted with the vastness of creation and reminded of our own small place within it. Yet in that very confrontation lies something uplifting. By seeking answers in the darkness, we join a grand human story of discovery that spans generations. The universe remains a place of mystery and wonder, and we are privileged to witness it and to inch toward understanding its secrets. To be the species that can reflect on these cosmic mysteries, and perhaps one day unravel them, is a gift of consciousness that we cherish. One day in the future, it's possible that a breakthrough will occur. Perhaps a detector, deep underground, will register an unmistakable dark matter interaction, or a space observatory will discover a subtle pattern in distant starlight that can only be explained by new physics. When that day comes, the news will ripple across the scientific world and beyond, turning what was once theoretical into something tangible. We can imagine the excitement as decades of speculation solidify into real understanding. Physicists would race to verify and explore the details of the discovery, while the rest of us might look up at the night sky with a renewed sense of connection. We would know a little more about what the universe is made of, and what we ourselves are made of. And with that knowledge, the darkness would become just a bit more familiar. It would almost feel as though a new sense had awakened in us, one that can perceive a layer of reality we never could before. Ultimately, the hunt for dark matter and dark energy is a tribute to the boundless curiosity of our species. We find ourselves in a universe full of questions, and we thrive on seeking the answers. Not having all the answers is not a defeat. It is a driving force that propels science forward. The unknown is not a void to fear, but a frontier to explore. With each experiment, each observation, each new idea, we chip away at the darkness, bringing a bit more of the universe into the light of understanding. We stand today on the cusp of discoveries that could redefine our view of reality. And even as we strive for those breakthroughs, we cherish the mystery that remains. For it is the mystery that makes the universe such an endlessly fascinating place. It ensures that there will always be new horizons to explore and new questions to inspire us. The shadow universe, this vast unseen realm, beckons us onward. And we will continue the journey, guided by our wonder, our humility, and the quiet certainty that searching for truth is its own great reward.